Good morning, everyone. I think we'll kick things off to keep on schedule. My name is Philip Ball. I'm chairing this hot topic. When I was asked to try to convene a panel on quantum computing for this event, I never dared dream that I'd be able to get this fantastic group of speakers of this caliber to come along. But they did say yes. And in fact, one of them, John Martinez, said yes because he'd been told by one of his graduate students how wonderful the Heidelberg Laureate Forum is. So there's a good advert for you. The word is getting around. As I say, the session is going to look at quantum computing. I used to feel as a science communicator that it was my duty to try to temper the sort of breathless reporting about quantum computing by telling people that, no, you're not going to be able to get a quantum laptop, next year or in the next 5 years or whenever. The way that things have developed, particularly over the last year or even 6 months, makes me feel that it's still my duty to say that, but that having seen the developments that are taking place, and in fact also having stopped by at IBM Zurich yesterday to see their quantum computer, I think that the message is more that what's going to happen is more profound than that. It's more profound than that you're going to have a quantum laptop that's faster. And there is no better selection of people to tell you about that profundity than the people we have to talk to you today. Just 3 talks before lunch, then 2 after lunch, and then at the end of the session we'll have half an hour of a panel discussion with all the speakers. So there won't be any questions after the individual talks. Save them up for that panel discussion at the end. It'll just be half an hour, I'm afraid, but I hope we can cover a lot of ground then. So I'll hand you over to these folks. There is really no one better to tell you, I think, where this field is going to go in the near future than the speakers we have today. And the first of them is Scott Aaronson, who is Professor of Computer Science at the University of Texas at Austin. And his research interests include quantum computing and theoretical computer science more broadly. And he also writes an influential blog called Shtetl Optimized. I just took another look at it recently to refresh my memory, and I thought, God, I'm going to have to read all of this. It is fantastic, so do take a look at that. Scott's talk is Complexity Theoretic Foundations of Quantum Supremacy Experiments.
So thanks. It's a real honor to be here. So what I'm going to talk about is joint work with a bunch of students, most recently with Li-Ji Chen, and it's about this something called quantum supremacy. This term was coined by John Preskill in 2012. In retrospect, it's probably not the best choice of term. I got a lot of humor mileage about it for a while in giving talks. Like, am I going to disavow support from, quantum supremacists and so on? And then, somehow November of last year, it all stopped being funny. But we're kind of stuck with the term. So what do people mean by it? What it basically means is just, the way I think about it is, there are, different applications of quantum computing that you may have heard about. One of them is breaking public key crypto systems, such as Diffie-Hellman and RSA. One of them is, getting probably square root type of speed ups for optimization and planning problems. One of them is simulating quantum mechanics itself, designing better drugs or designing better nanomaterials by, being able to simulate complicated quantum systems. That's probably the most important practical application of quantum computing still today that we know about. Then there are potential applications to machine learning and other things. But to me, none of those are really why I'm in the field. I like to say that for me, the #1 application of a quantum computer is simply to disprove the people who say a quantum computer is not possible. Okay? I get, Philip mentioned my blog. I get these people coming on my blog all the time saying, well, look, obviously, this is never going to work, maybe because quantum mechanics is wrong, or there's some new principle on top of it that would prevent a quantum computer from ever scaling. And I like to say to those people, well, I hope that you're right, because if you're right, that would be a revolution in physics. That would be 1,000 times more exciting than a mere success at building a quantum computer, which is, I think, sort of the more conservative possibility, okay? But either way, we would like to find out the truth. We would like to know, can this, really be built? And of course, not just, in principle, but in practice. So sort of quantum supremacy means sort of targeting that application. It means trying to experimentally test the extended Church-Turing thesis, which is the statement that, any physical system, that you find in nature could be simulated by a standard Turing machine with at most polynomial overhead. Okay, I think that's been a hugely influential thesis because it's actually really, really hard to find a counterexample to it. And I think as far as we know, based on the known laws of physics, quantum mechanics seems like it may be the only counterexample to that. Okay, but we would like to know, is this a counterexample that can actually be realized? Okay, now of course, the extended Church-Turing thesis is an asymptotic statement, right? It talks about what could be simulated with polynomial overhead, and so no asymptotic statement can ever be, truly proved or refuted by a finite number of experiments. Right? Even if we did build a quantum computer that factored million-digit integers, a determined enough skeptic could say, well, I guess the constant factors are really screwy. But we would like to sort of increase the strain on, on any kind of view that says that quantum computing is not possible by really doing something at a large scale and doing something that we can be as confident as possible is hard to simulate with a classical computer. Okay, and so this really changes the focus because we don't care anymore about doing something useful. Okay, forget about usefulness. At least for the time being. I don't, you don't repeat it too loudly to the funding agencies. Okay, but that's the truth. Okay, let's focus instead on just being as certain as we can that we're doing something that's hard, that is hard to simulate classically. Okay, and the trouble is, well, we're never going to have like an absolute proof that, or, at least, it seems too much to hope for that we could prove that our quantum computation is hard to simulate classically, right? Because, we can't even prove that P is not equal to P space, or, if there are things of that kind. Okay, but let's try to, base, our belief in hardness on sort of conjectures in computer science that are as solid as we can make them. Okay, so that's really what this talk is going to be about. Okay, so now an important realization that a bunch of us came to around 2010 or 2011 is that if this is your goal, just getting a speed up with a quantum computer that we can be as confident in as we can, well it changes a couple of things. Okay, one thing which is good news is that you don't seem to need a universal quantum computer to start seeing, a quantum computer that can do something which is classically hard. So it may be actually a much, much easier as a technological proposition to build a device that does something that's something useless but classically hard than it is to build a fully programmable quantum computer, okay? And there have been, a bunch of proposals along these lines. So one of the first was called Boson Sampling, which was proposed by my student Alex Arkhipov and I. I'll tell you a little bit more about what that is. Simultaneously, there was something called instantaneous quantum polytime, IQP, by Bremner, Joza, and Shepard, closely related to something called Fourier sampling. And there have now been several other proposals along the same lines, none of which seem to require a full universal quantum computer, but could be implemented in the lab using technologies that are closer on the horizon. Okay, but now the second change that, the type of problems that we're able to solve with these near future technologies are typically not decision problems, right? So they're not the kind of conventional problem that you would study in theoretical computer science, where your question has a definite yes or no answer, and you say you're just trying to decide it with a small probability of error. Instead, these problems tend to be sampling problems. So they're problems where you are told some probability distribution, say over n-bit strings, and now your task is just to output a sample from that distribution, say either exactly or more realistically, approximately. Okay, so they're not problems with one right answer. They're problems where, in order to test whether you're solving it or not, you would have to collect, many outputs and then do some statistics on them. Okay, but what it turns out is that when we switch attention to sampling problems, well, we get two things. One is that many of them are easier to solve with near-future quantum devices, as I mentioned earlier. Okay, but a second advantage, which sort of comes as a bonus, is that these problems, we can often be more confident that they really are hard for a classical computer than we are in the case of the decision problems, like or problems with a single valid answer, like factoring and discrete log. Okay, I like to joke that if there if a fast classical algorithm, say for factoring or discrete logarithms, were discovered tomorrow, well, that would now collapse a large part of the world's digital economy. Okay, but on the other hand, collapsing the world's economy in some sense is not that impressive, right? I mean, there are many other ways to do that. In the U.S., we're working hard on it right now, right? But what's more impressive to a theoretical computer scientist like me is to collapse the polynomial hierarchy. Okay, and factoring is just and discrete log are just these two specific problems. If they fail, they don't really bring anything else with them. Okay, but so it's not like if p would equal np or something like that. Okay, but the polynomial hierarchy, well, for those who don't know, what it is it's just a generalization of the classes p and np to involve more quantifiers. So you could ask things like, for every setting of these variables, does there exist a setting of those variables such that for every setting of these variables, this formula is true? Okay, and if I have k alternations of quantifiers, we say that's the kth level of the polynomial hierarchy. Okay, so for the a standard belief in computer science is that hierarchy is actually infinite. That the more quantifiers you have, the more problems you can solve. And if that hierarchy would collapse at any level, that would in some sense be almost as bad as p equaling np. Okay, just at a higher level up. So what we'll see is how we can base our belief that quantum mechanics is hard to simulate with a classical computer on things like the polynomial hierarchy being infinite. Okay, sometimes literally that, sometimes it won't be quite that good. Okay, but a sort of very, very generic beliefs about computational hardness. Okay, so we merely give up on, well, practical applications, and it will also become, so that verifying the results of the computations will itself be a very hard problem. Okay, and that is why, well, as you're going to hear from John Martinez's talk, we are looking in the near future to target a range of, let's say about 50 qubits. Okay, 40 or 50, that's a range where classical simulation is very, very difficult, we think, taking like 2 to the 40 or 2 to the 50 time, okay, but it's still possible. And it better be possible because we need it in order to verify the answer. Okay, we won't be solving NP problems like factoring where the answer is easy to check once you find it. Okay, so a simple example is a task called Fourier sampling, which just involves this quantum circuit right here, where I would start with a collection of qubits, say all in the 0 state. I would apply what's called the Hadamard Gate, which is just a gate that puts you into a quantum superposition of the 0 and 1 states. So if I do that, I make an equal superposition over all 2 to the n possible settings of these n qubits. Okay, that's actually very easy to do with a quantum computer, right, to create these enormous superpositions. The hard part is to do something useful with it, okay, because that requires sort of choreographing a pattern of constructive and destructive interference. Okay, but now, we could do that. We could apply some Boolean function, say flip the amplitude of each basis state, if the Boolean function evaluates one way and not if it evaluates the other way, then Hadamard all of our qubits again and then measure them all. And the end result of that is that the probability of observing each specific output string, z, will be equal to the squared Fourier coefficient of z when we look at our function f in the Fourier basis. Okay, and now what's interesting about this is that, well, this is a sum of exponentially many terms. Okay, if this function f were given to us explicitly, say by some circuit to compute it, then this is what we call a sharp P hard problem, complexity class invented by Les Valiant, who's here, and and sharp P we believe to be even much harder than NP. Okay, and so you say, wow, quantum computations can encode sharp P complete values in their amplitudes. That seems super duper mega powerful, right? Okay, but there's a catch here, which is that these sharp P quantities are not directly observable, right? In quantum mechanics, you don't directly observe an amplitude. Those are just the numbers that you use to calculate the probability that you're going to see this outcome or that one when you make a measurement. Okay, but in this case, the fact that this exponential sum shows up even as an amplitude, already has computational consequences. And the reason it does is that this is a sum of both positive and negative terms. Okay, and those kind of sums that sort of mostly cancel each other out, and you're just trying to estimate the little residue that's left over, okay, they have the property that even estimating them is already a sharp P complete problem, okay? And that's a really key property. Why is that important? Well, because it turns out, using tools from classical complexity theory, it's possible to show that if I had a polynomial time classical algorithm that could sample from the same probability distribution that this quantum circuit was sampling from, then I could just, and I say I want to estimate for what fraction of random strings will my classical simulation algorithm output the string z, let's say, right? Then this is something called approximate counting, which is known to be solvable in the complexity class called BPP to the NP, probabilistic polynomial time with an oracle for solving NP complete problems. Well, that sounds pretty super powerful. Okay, but the point is, if our beliefs in complexity theory are anywhere close to correct, it has to be not as super powerful as P to the sharp P. Okay? But if this type of experiment were efficiently simulatable by a classical computer, if a classical computer could even just sample from the same distribution that the experiment does, then the conclusion would be that P to the sharp P would equal BPP to the NP. If you don't know what that means, well, it's bad. Okay? Among other things, it would mean that the polynomial hierarchy would indeed collapse, in this case to the third level. Okay, so based on very general beliefs in complexity theory, there are very simple quantum experiments that should be hard to simulate classically. Okay, so boson sampling was sort of an early, I guess, work where we made that point explicitly, and we pointed out that that actually solving this sort of hard sampling problem doesn't even require like a full quantum computer that could manipulate qubits and so forth. In fact, it's enough if I have like a quantum analog of what's called Galton's board, which is something that's on display in many science museums, where I just would throw balls into a lattice of pegs and just look at how they bounce around. In this case, they fall in a pattern that approximates the binomial distribution. Okay, now the quantum analog would be, instead of balls, I have photons. Instead of pegs, I have beam splitters. Okay, and this can lead to very interesting effects, like one called the Hong-O-Mandel dip, where I shoot 2 photons into the 2 arms of a 50-50 beam splitter, and then I find that actually where they come out at the bottom becomes perfectly correlated. So with half probability, both photons go in this arm, and with half probability, they both go in that arm, even though they never interacted, right? So what gives? Okay, so like with pretty much everything else in quantum mechanics, the answer involves the magic of minus signs, of interference of amplitudes. Basically, there are 2 contributions to the amplitude for the photons to go down separate arms. One where the photons go like this, this one goes here and this one goes there, and one where this photon goes here and this one goes there. Okay, but one of those paths contributes positively to the amplitude and the other contributes negatively, so they cancel each other out. Okay, more generally, we could consider a situation with n photons. Okay, and what you find then is that the amplitude for the n photons to go from a given input state to a given output state is given by a function of an n by n matrix called the permanent. Okay, that's this function here. It's just like the determinant, except without the minus signs. Okay? By the way, if we were talking about fermions instead of bosons, the other type of basic particle in nature, then it would be the determinant. Okay? But so Avi Wigderson once joked that that the bosons should sort of sue for having for having such why were they saddled with such a harder problem to solve? Okay? So the determinant is easy to compute, but the permanent, of course, Valiant proved, is sharp P complete. Okay, and so you can quite easily, you can set up a physics experiment involving a bunch of photons passing through a network of beam splitters, and to calculate the probability of the photons landing in any given output configuration, you would have to take the permanent of an n by n matrix if there are n photons. Okay, now what is that good for? Well, we have no idea. Okay, but we were able to give evidence that even taking this sort of simple optical system and simulating it with a classical computer would be hard. Okay, it's certainly hard in the sense of the previous slide, but in fact, we went further and we said, under very plausible conjectures in complexity theory, this type of thing should be hard even to approximately simulate. Okay, so the main theorem that we proved is that if there were a polynomial time classical algorithm that sampled from any probability distribution, which was even close in variation distance to the ideal distribution that this experiment samples from, well, then what that would mean would be that you could take a random matrix, which let's say means, a matrix of independent Gaussian entries of mean 0 and variance 1, and you could approximate its permanent in this complexity class BPP to the NP. Okay, now, our conjecture, if we were not able to prove, is that that problem of approximating Gaussian permanence is already sharp P complete. Okay, if so, then even a noisy simulation of this experiment would collapse the polynomial hierarchy. Okay, that remains an open problem. Okay. We were lucky in that at the same time that we were thinking about this, there were all these experimental quantum optics groups who were just sort of looking for something to do. And they just kind of ate this up. And they said, hey, these bosons that you're talking about, they actually exist in the physical world. And we can try this out. And so there were a bunch of groups that did experiments with, boson sampling with 3 photons. Long story short, the result of the experiments is that quantum mechanics is true. The amplitudes are given by 3 by 3 permanence. Since then, it's been scaled up to 6 photons. Okay, scaling it up more is a hard technological problem just because we don't have very good single photon sources at the moment. Okay, but if you could scale this up to, let's say, 30 photons or 40 photons, then you're doing something that really starts to get hard to simulate with a classical computer. And in fact, I just came here from a quantum optics conference in Rome where there are lots and lots of experimentalists talking about how to do exactly that. Okay, but in the meantime, what you're going to hear from the other talks today is that, there are people doing other things like superconducting qubits where they are, expecting in the very near future to have about 50 very high quality coupled qubits. Okay, now again, 50 qubits is probably still not enough to do anything useful, at least that we know of, but it should be enough to do something that's hard, okay, to do one of these quantum supremacy demonstrations. And so what we've been thinking about in our more recent work is, well, what could you do with these sort of 50 qubit setups, that is hard to simulate classically? And once they've done it, how should they verify the answer, right? What tests should they apply to be sure that they really were, doing something that's classically hard? Okay, so, the main sort of proposal that we have is sort of, embarrassingly simple. It's basically you take your collection of qubits, let's say it's a 7 by 7 array, and you just apply to them a random sequence of quantum gates. You pick, let's say, fix once and for all some random sequence of quantum gates, as deep as it can be while keeping everything coherent, and you apply that. And then you measure your qubits and you see what happens. You repeat some number of times, okay? Now, each time you repeat the experiment, you'll get an independent sample from some probability distribution over, in this case, 49-bit strings. Okay, and that distribution, will be basically a total mess, right? It's, but the important point is it will not be the uniform distribution. Okay, so some outcomes will be a little bit likelier because of constructive interference. Others will be somewhat less likely because of destructive interference. So, you'll have constant variation distance from the uniform distribution. And now, your quantum computer can sample from that distribution, and you can now challenge the classical skeptic. Well, can you sample from that distribution? No, you can't? Well, okay, we're doing something faster. It's like the quantum computing version of the Bell inequality, if you like. Okay, so then, how would you check if you were sampling from this distribution? Well, the basic idea is you apply some statistical test to the outputs that you observe. Okay, so you wouldn't have to repeat the experiment an exponential number of times. But we're not asking you to characterize the distribution. That's too expensive. Okay, but just repeat the experiment, let's say 1,000 times, get some representative sample of outputs, and then for each of them, calculate what would be the predicted probability of sampling that according to, your distribution D, and then check whether the outputs that you've observed are biased toward the ones with larger probabilities in the way that would be expected if you're doing correct sampling. Okay, so it's a statistical test, but now this leads to, its own question, which is, well, if we say that this is the test that you're applying, well, then maybe there could be, if you believed in some classical conspiracy theory, that there's no real quantum computing happening, well, maybe there would be some way for a classical gremlin inside of your device to just pass this statistical test without sampling from the hard distribution, right? Who knows? Okay, so what we did, in the new work was actually to try to rule even that out. Okay, so we made an admittedly strong hardness assumption. Okay, our hardness assumption, well, you can read it here, but basically it says there's no polynomial time classical algorithm which would take a random quantum circuit from your ensemble with n qubits and m gates, m being larger than n, and which would guess whether a given the probability of a particular output, let's say of the all zero string, was greater than or less than the median of all 2 to the n of the probabilities, and which would do that with even slightly better, with even a slight advantage over random guessing, like a 2 to the minus n advantage, n being the number of qubits. Okay, I admit that's a strong assumption. Okay, in fact, one can get an advantage over random guessing that is 1 over exponential in m being the number of gates. Okay, but remember that's much more than the number of qubits. Okay, so we conjecture that getting this kind of advantage is hard. Okay, and now a theorem that we prove says that if you grant that assumption, then if you consider this random quantum circuit sampling, then not just simulating it with a classical computer, but even doing anything whatsoever that passes some simple statistical test on the outputs, is already going to be classically intractable. Okay, so I'm running out of time, so I won't be able to show you the proof of this theorem. Well, here it is. It fits on one slide, the proof, okay, and it's a reduction. So, like everything else in theoretical computer science, you assume that by way of contradiction, that, you had a fast classical algorithm that could pass your test, and you show how, by using that, you would violate the original assumption, which did not itself talk about any sampling problems, but was just about a decision problem. Okay? So the next thing we did is we looked at what is the best classical algorithm to simulate quantum circuits. That, of course, is a very old question. But what we noticed is that there were sort of two approaches that are sort of complementary to each other. If you're trying to simulate quantum mechanics with a classical computer, there's what we could call the Schrödinger approach, which says you just store the entire quantum state on your classical computer using 2 to the n memory, if I have n qubits, also about 2 to the n time, because then I just do a bunch of matrix vector multiplications. Okay, or if I want to use less memory, then there's also what I would call the Feynman sum over histories approach, where I use only a linear amount of memory. Okay, but now the amount of time that I need is greater. It grows exponentially, not just with the number of qubits, but with the number of operations. Okay, and that can make a huge difference in practice. Because like if I'm Google, I could handle 2 to the 40, but I can't handle 2 to the 1,000. Okay, and the numbers we're talking about now are like 40 or 50 qubits, but thousands of operations. Okay, so we wondered, is there an algorithm that somehow gets the best of both worlds? And we found that there is something close to that. Okay, there is an algorithm to simulate a quantum circuit with n qubits and depth d, which uses time that grows like d to the n, and that also uses a polynomial amount of memory. Now, the way that we give that algorithm, for anyone who knows classical complexity theory, it's basically just Savage's theorem. Okay, it's a recursive divide and conquer construction. I don't know why this wasn't noticed earlier. Okay, but it seems to be new. Okay, but the main point is that all these algorithms, each of them has a reason why it fails to violate our strong hardness assumption. Okay, so we still don't know whether you can do this guessing with a 2 to the minus n advantage, over random, and that remains a challenge that we leave. Okay. So we did other things in this work, about sort of the general form that a quantum supremacy theorem can take. So we showed that sort of any strong quantum supremacy theorem of the sort that we hoped for with boson sampling would have to be non-relativizing. Okay, it would have to fail relative to a suitable oracle. Okay, so, this was a quite hard oracle to construct, but we did that. And then we also showed that quantum supremacy is possible relative to efficiently computable oracles, the oracles with small circuits, under merely the assumption that there is any one-way function. Okay, so to summarize, in the near future, we may be able to do random quantum circuit sampling with around 50 qubits, and you'll hear more about that shortly. Okay, but a central question for us theorists is, well, how do we verify that something classically hard was done? And I think that we would be urgently called upon to think about this because of the progress in experiments, even if there were nothing theoretically interesting to say about it. So it's fortunate for us that I think there is. Okay, thanks.
Thanks very much, Scott. Well, I'm going to try to keep to schedule plus 5 minutes, so I'll be very brief. Clearly, as Scott has said, we don't have to get too hung up on doing something useful with quantum computers at this stage, but nevertheless, you can, and I think Jay is going to tell us something about that. Jay Gambetta is manager of the Theory of Quantum Computing and Information section at IBM's T.J. Watson Research Center at Yorktown Heights in New York, and his title is Approximate Quantum Computing with Near-Term Devices.
I'm going to tell you a bit about the work that we're doing at IBM. I like Scott's ideas, but I think that's still a bit further away from where we're at now. So why is it interesting? Well, to me, why people are starting to think of this as a hot topic is we're moving from this period where a lot of experiments were just single 2-qubit experiments demonstrating foundations, to experiments that are starting to get really big, starting to interest computer scientists like Scott, and we're starting to bring these two fields together. That being said, we're still at this point, and I like to show this slide because there's a picture of the early classical computers, and this is what it looks like in the lab. Still a lot of cables, a lot of things going on, but it gives us some context of where we are. So I like that we're seeing this transition from, most people and everyone agrees that long-term we want to get to this thing that we like to refer to as universal fault tolerance. And this is the idea where you'll have a quantum computer, you write an algorithm, it performs the algorithm as expected. This requires error correction. At that limit, there's a lot of overhead to keep these qubits protected. And there's a lot of miscommunication with a lot of people thinking logical qubit equals physical qubit. And really, that's not true. In these algorithms, like Shor's algorithm, that they explain within the context of universality, they are really implying on logical qubits. So I don't want to say this is a different model of computation, because it's not, but the way I like to think of where we're going at the moment is trying to think what we can do with a device that is faulty. And for that reason, I like to call it approximate. The goal is to try and eventually demonstrate something where it has an inherent advantage over classical computers, or to find a way and a path to seeing where an advantage will be before we get to the path of having fault tolerant. Numbers are here, I'm not sure, but it's some interesting number that's beyond what we can do. So what do I mean by a short depth circuit? Well, I just simply mean something that can be run within the coherence time of the devices. It comprises of a lot of single and 2-qubit gates, and we simply just count the depth of how many of these can be done along. So we're trying to understand what can be done with this type of stuff, and this is what I'll focus on throughout the talk. But before I get there, I just wanted to say we've done a lot to also enable people like you, to enable people that are not got a lab to come and actually start to use our equipment, starting to try and think of what the language should be. First off, in 2016, we put a 5-qubit system online. You guys can go there, program it, play it, run your own quantum experiments, experiment with placing these single qubit gates, measuring. And since then, it's been pretty successful. There's been over 50,000 users, 500,000 experiments, and about 30 experiments that have papers that have been written by other people, not us. Sorry. Does this sound better? All right, so where are we gone now? Well, this web interface is just a toy. So what we've spent a lot of time doing is really starting what we want to see as an open source Python repository where you can actually go to GitHub, you can download our first version of an SDK where you can start to program these devices. You have the freedom to run the gates, experiment over it, contribute to it. I don't know what the first quantum hello world program would be. I like to think it's going to be something like creating a Bell state or something like that. But these tools are in place, and I invite you guys to have a look. Some simple things you can go do is things like measure your, a measurement spelled wrong, but measure coherence of a quantum system, make a Bell state, show a violation, a Bell's inequality, measure the state tomography or process tomography, and many more. But let's get over to what our systems look like. So we're working with superconducting systems. I don't really want to explain exactly what these are, except to say you can think of these much like a mass in a spring, okay? The charge here represents some mass object, and this little junction here is an inductor. This inductor takes two values depending upon the superconducting electrons that travel across it. Because it has those two values, there becomes two levels that are well separated. That becomes our qubit. The way microwave pulses are done to do the gates is we simply vary the external microwave field of some amplitude and phase. And this allows us to do an arbitrary rotation around this thing that we like to call a Bloch sphere. You can think of this as my ability to do any single gates. Okay? For the 2-qubit gate, it's a little bit more complicated, but it's pretty easy to understand. Our system, the way we do it is we drive this qubit at that one's frequency. So what happens is, depending on the state of this qubit, it acts like a little impedance mismatch. And you can think of this as a quantum filter. And so the field quickly goes through, and it drives this one at a different rate depending on the state of this one. So you get this conditional rate. You get this ability to do something different to the other one depending on the state of the first one. And that becomes our building blocks that we like to use. And some of our devices, here's a 16-qubit device showing the 16 qubits connected by these buses and these readout ports coming in. So what are we trying to do with it? Well, the first thing, and one of the most important things, is to prove that these systems are truly quantum. Like Scott, we agree that you want to do to prove verification, you want to do something like start with some initial state, do some circuit, and then sample from it. We like to define a quantity that we call the quantum volume. The only reason we do this is to take the emphasis off it just being the number of qubits. To point back that as we're going to make progress in these devices, both how long the circuit can be and how wide the circuit matter. Taking an inspiration from Scott's, we also we do our analysis for characterization of these devices by doing something where we apply a uniform permutation, and then we apply an arbitrary unitary over 4 qubits, and this is an SU4. We allow this to be done independent of the device. That way it's sort of hardware agnostic. Your compiler will compile down to different devices. If you have more gates, you get a better number. If you have more gate sets, you can easily represent these unitaries faster. And it basically tries to take all of these out of the equation. Then we can look at the quantity exactly that Scott was talking about. And here's a case where you run a simulation that consists of 6 C-naughts on 5 qubits, and you see there's a lot of features, as Scott was talking about. You run this on the experiment, and those features are present. When you get up to something like 40 C-naughts and compare it, it really starts to lose these features. So you can plot this quantity, and you can look at it, and you can see it decay as a function of the depth for the different numbers of qubits that are considered. And taking the point of about 2/3, you find that for this system, we can really only exploit 3 qubits of this to really say we are fully controlling the 3-qubit Hilbert space of this. The same is also true when we go to the 16. The current error rates of our systems are just not enough to really exploit very long depths. And when you randomize over all different permutations, I've only shown one for each of these, you find a similar type of plot, and you find that it's agreeing with the depth 3. There's even an odd thing that's going on that I can go into if anyone's interested. So after we've tried to characterize, what do we want to try and do? Most likely, people believe that the first applications will be something in chemistry. We too have a similar view. So we want to look at heuristic algorithms to start with and just see how they perform with real hardware and adapt our hardware as we learn with this approach. So an interesting problem that's been around for a long time is to find this energy. So you got some Hamiltonian, you got some wave function, and you want to find some energy that represents the eigenvalue of this. This is just a simple eigenvalue problem. Now, turns out that this wave function might be too complicated to represent on a classical computer. So the hope is that we can use this system to represent the wave function to evaluate the cost function, and then use some classical computer to go backwards and forwards, changing the parameters, changing the different types of wave functions we generate until we find the lowest energy and exploit this. Mathematically, you can just show that, this said another way, you have some Hamiltonian that you parameterize in terms of some small number of parameters that can easily be measured. You have some ansatz for your trial function that is in terms of parameters that are easy to do within the short depth model. Here, these are these single qubit gates, and this would be some entangling operation. You get your energy by sampling the output and putting it all back together to estimate some energy, and then you just keep repeating and going through. So experimentally, you find out this Hamiltonian, you take a fermionic model or something, you go through a transformation that maps it to qubits. This is, you can show that is constant with the number of orbitals. You find your controls, and you implement this repeatedly. We've implemented this here. And here we've looked at the H2 molecule. So each one of these points starts with a given description of the Hamiltonian, which when you map it to something in terms of qubits will have some answer, some description. Here is the value at this, the blue point. Here is the value at the red point. So each one of these you'll start to minimize. It'll minimize to some value. Then you'll go to the next point, and you can efficiently find the Hamiltonian, you'll minimize it, and you can just map out this orbital. This orbital is important for people in chemistry because from this they can predict things like reaction rates and things like that. So looking at this, you see that this quantum computer predicts pretty reliably this potential. So recently we continued this and we applied it to lithium hydride and beryllium H2. And what you see here is you can map out the potential, but you see some interesting features start to emerge. This was just recently published in Nature. You see this, for instance, here you see this divergence point. This is due to the fact that the depths of the circuits were too short, and the eigenvalue solver got mixed up between which value of the eigenvalue to go towards. So there's some creativity that you have to come up with better parameterizations and things like that to choose that you go to the right one. Later on, there's just too much noise that it starts to mess up the system, but all of it is well described because these systems are small enough, we can simulate it in an evolution, including noise. So this was one of the first demonstrations that really tried to map out and look at the potentials of these molecules. So where do we have to go? Well, we have to try and reduce these errors. One way that we've been thinking about to reduce these errors is what I like to call error mitigation. See, error correction tries to take this quantum state and make this quantum state more pure, which is what you'll need to do in the end. But if I'm only interested in an observable, is there some way that I can make that observable have more fidelity to what it should be without fully purifying my state? And taking some ideas from just numerical analysis, if I want to estimate some quantity and I don't know the errors, but I can double the way I look at that, say it's a differential equation, I can double the spacing between the way I look at it, I can add different orders together to suppress the next order, and polynomially keep reducing it. So what we so this is just written here, is you come up with some Richardson extrapolation that says you get your final energy that is a function of this unknown noise as a function of different sampling points, different ways that you've scaled the experiment with some weighting coefficient, and you can show that the bound on the energy is related to the next order. Doing some numerical simulations as a function of this error rate p, so down here is much smaller error rates, we have the first order answer, we have the second order, third order, and fourth order, and we can show for this type of noise, which we refer to as depolarizing noise, there's no direction to it, it works to improve it. For this type of noise, which is typical in superconducting qubits, it's what we refer to as amplitude damping and dephasing. We see the same type of effect, and also noise where you imagine that your system is coupling to other qubits, and you don't know the state of them. You can see a similar type of effect numerically. So trying this experimentally, for this H2, we can see that we get this improvement. So if we take our estimates for this C equals 1 case and C equals 1.5, when we combine them together, we get much closer to the exact value. And these are different realizations. This one didn't work out for reasons that we're still investigating. And you can see that on average, the way of combining together gave us a much better estimate of this observable. So we're hoping for these cases where when you want to just run this algorithm and all you want to get out is some observable, this is a method that can be used. I don't want to say that you can also speed up classical problems because, like Scott said, it's most likely only going to have a polynomial speed up if there is one at all. But you can just blindly run your favorite MP problem, be in this case max cut, where the idea is you have some graph and you want to partition these into colors. And you can see that when I run this over on the quantum computer, if I don't allow my system to entangle because of the way I constrained it finding the eigenvalues, it fails to find the solution. But allowing it to entangle, we see that it has the ability to find the solution. It's an open question how this form of this variational scales and how this relates to what Scott talked about with or mentioned with the QAOA. And these are the questions that we're interested in. The last area that we need to keep going and we need to understand is eventually we're going to have to design codes on these systems. We're going to have to design methods that we can remove the errors from it. Most error correction codes are designed in a way where the errors are assumed to have a certain form. So we want to look at small experiments to get an understanding of what's going on and understand the concepts of error correction and fault tolerance. So generally speaking, in quantum systems, you can't clone a system. There's no way to take some system and map it to 2 copies of it. So you have to come up with some way that you take a system, you encode it to spread the information over many degrees of freedom. You imagine some error comes in and applies to your system, and then some wizard comes along with some way to work out what's going on and fixes it, and you get back your quantum system. So with these small systems, you can start to look at small codes. The smallest code that is not really an error correction code, but is more an error detection code, is known as this 422 code. I'm not really going to go into the details of it other than to say you have basically some syndrome that you want to extract some global measure from it. So here I have this circuit that allows me to measure the ZZZ operator of all these qubits. And from that, I can infer where an error occurred. For instance, if an error occurred here, I would see that it would make an error here, but this error would be detected when I measure it here. There are errors that are undetectable. For instance, if an error occurred here, it makes 2 errors, and these 2 errors are equivalent to the logical operation, so I can't detect this error. So there's this notion of trying to understand what errors matter for the code, how do we look at it, that we're trying to investigate. But you can run an experiment where you simply start by initially preparing these logical qubit, you wait for some amount of time, and then you measure the errors. And you can see a decay. This decay looks close to being exponential, but if you zoom in and look really close at the top, you see this deviation. This deviation is the start of trying to see that the code is pushing the error rate from linear to the quadratic form. And it's really trying to, what we really need to see is this pushed along more to allow us to say that we're starting to really protect these systems. So, oops. Sorry, got an error. Yeah, so I think the way I would like to basically summarize is with these systems, what I want to start doing and what we're looking at is we want to study these Morse codes, understand the path to making bigger systems and how that works. We want to look at these heuristic algorithms, namely in optimization chemistry and machine learning, and see and understand when they have an advantage, and if they do, how can it be used. We want to really understand, are there ways that we can remove errors without the full overhead of error correction so that we can get better results in these near-term devices? Work out how to verify and validate these quantum devices, come up with ways that we can keep proving to ourselves that we're making progress and increasing the amount of the quantumness that they can explore. Also learning about exactly where these errors are coming from. And then eventually try and demonstrate a quantum advantage or supremacy, whatever your favorite word is, to say that there's something about these systems that cannot be explained classically. And that's where I'd like to end.
That's great. Thanks very much, Jay. That's kept us on course as well. I think one of the striking issues about quantum information as a field is that I think it challenges the prevailing view, I think a misleading view anyway, that science works by going from pure to applied. And we can see that you can do applied things with quantum computing, but quantum information is also a fundamental theory, and I think there's no better person to tell us about how those two things come together than Seth Lloyd, who is a professor at the... In fact, Seth, it's always sort of intrigued me that you're a professor in the Department of Mechanical Engineering at MIT, which I think also exemplifies the fact that actually you can come at this angle from anywhere you like, and that it actually challenges the traditional sort of distinctions we have between disciplines. So Seth's title is Quantum Computers in Society and in the Universe.
Thank you very much. It's a great honor to be here, and a little intimidating because every single person in this room is mathematically more sophisticated than I am, which is kind of scary. Actually, the reason I'm a professor of mechanical engineering is that no physics department would offer me a job. It's pretty simple. But now I can just be a professor of quantum mechanical engineering, which is better, or even a quantum mechanic. If your quanta are broke, we fix them. So for a fee, a large fee, which actually is rather true right now, because one of the interesting things about quantum mechanics, quantum computing in society, is that we're now in a funny era, which has just really happened in the last few years, where not only are companies like Google and IBM and Microsoft and Intel and Tencent and Huawei and Alibaba spending lots of money on building quantum computers, but all these startups are popping up like mushrooms, which allows people like Scott and me to make money for consulting. So I feel that the right people are at least making money about this right now. So I'd like to talk about a rather specific aspect of quantum computing, how it fits in society. Here you see the title. This title is called Big Quantum Data. Why should we talk about big quantum data? Well, I'd like to talk to you about quantum machine learning, how you can use quantum systems to find patterns in data that you could never find classically. Why? Well, for one thing, everybody's talking about big data these days. You can't get a grant proposal unless your grant talks about, big data. And then the other reason is that the other way to get a grant proposal funded is to have graphene in the title. So now we can have a grant proposal that says something like, graphene-based quantum random access memories for the analysis of big data, certain to be funded. All right. So I'd also like to bring this up because I talk about this because it struck for this particular audience that there are a number of open questions which are mathematical in nature. And if you actually look at the main problem in quantum computing these days, it is not, in fact, the technological problems of building quantum computers, daunting though those may be, as Jay's talk indicated. It's that we need more algorithms for applying these quantum computers, particularly for the kinds of small, relatively small, 50 to 1,000 qubit quantum computers that are operating without full-blown error correction that we're likely to have in the next few years. And as Scott has pointed out, one thing we could do with these is to exhibit quantum supremacy, a hateful word. Supremacies, I hate it. Supremacy is all about hate. But perhaps we could turn it around. And I'd like to close at the end by talking about the possibility that not only can we use quantum systems to generate patterns that we couldn't generate classically, this problem of sampling that Scott was mentioning, but perhaps we could use the same kinds of quantum computers to recognize and classify patterns that we couldn't recognize classically. Because those of you who are familiar with deep learning know that very frequently the objects we're using to recognize and classify patterns can also generate patterns, and they generate and recognize the same kind of patterns. And the reason for doing this we can, instead of talking about quantum supremacy, we can have something called supreme quantum learning, which sounds a lot nicer. I mean, quantum supremacy, it's useful for us Americans because now the European Union has its billion-euro flagship program. The Chinese are investing 12 billion euros equivalent in quantum computing. We can always go to the government and say, we need to restore America's quantum supremacy. Again, I agree with Scott, this was more funny than before last November. If we have supreme quantum learning, we can actually use these quantum computers to do something useful. And the open question I'd like to raise is, can we actually do this with the devices we're going to have in the near future? Supreme quantum learning sounds like actually some delicious German dessert with lots of Schlag on top of it. All right, so let's look at there we go. So what is machine learning about? Well, machine learning is about things like, here are some examples of machine learning problems. There's classification and clustering. I'm sorry that the blue things don't show up here. Here are 3 clusters of different colors. And you're given, say, these 3 clusters. You're told that these are blue, these are red, these are orange. And now you're given a new spot, and your goal is to assign it to a particular cluster. That's an example of supervised learning where you're told what the classifications are before. Another example is handwriting recognition or pattern identification. Machine learning has gotten very trendy recently, and it's actually because it's started to be really useful. Machine learning, the notion of taking computers and using them to do data analysis dates back to the very first days of computers. Indeed, analog computers were used long before digital computers to do data analysis. The notion of actually building artificial neural networks and using computers to implement them date back to the 1950s with folks like Minsky and Papert and all those, and McCulloch and Pitts and these other pioneers in the field. And when I was a postdoc at Caltech in the 1980s, around 1988, I was working with Murray Gell-Mann, but I went to go talk with John Hopfield. This was at the time when, the biggest neural networks could maybe artificial neural networks could maybe distinguish between, 4 different patterns. And I remember Hopfield saying at the time, he said, I understand this is not doing very well right now, but if we had computers that were 1 million times more powerful and we had 1 billion times the data, this would work, I swear. And by gum, that's what happened, except we now have 1 trillion times the data rather than just 1 million times the data. Yeah, at MIT, in 2000, they replaced their switchboard operators with computerized voice recognition software. And for the next 5 years, the following would happen. You'd call up, the voice would say, whom would you like to speak with? You say, I'd like to speak with Professor Jane Smith. And then the voice would say, now ringing Mary Lefkowitz. If this is not the right number, press 9. Boop. Jane Smith. Now ringing Hua Zhang. Boop, 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 boop. This went on for years and years and years. And then finally, you probably noticed, just in the last couple of years, voice recognition software for things like smartphones has gotten to the point where it can actually recognize your voice. amazing. And this happened because they have billions of times the data. They combine sophisticated deep learning networks with methods for, tailoring their systems to your own personal voice. It works. It's amazing, right? But it took a lot. Excuse me. A particularly nice application of quantum machine learning is to look at topological features of data. Here is a data set. It has a hole. I think you'll agree, right? But how do you feed this into a computer and get the computer to tell you there's a hole there? Well, if I look up really close, why, it's all holes. There's nothing but holes. Well, there's a very beautiful method for topological analysis of data called persistent homology, which was, I think, first looked at by Gunnar Carlson at UC San Diego. I learned about it from Michael Nielsen. Which allows you to say, well, okay, let's make a simplicial complex out of this, connect things together, and then we'll apply methods of algebraic topology in order to find out whether there are holes in this system. And this is great, except the problem is that if I just have n points, finding all the higher dimensional holes, and for instance, the Betty numbers of the system, which counts the number of holes and voids at a particular dimension, takes time order 2 to the 2n. Which is bad. Whereas, as I'll mention, and I may be able to say a little bit about this, there are quantum computing algorithms for quantum computers that will will estimate the Betty numbers of a simplicial complex in time that goes as order n squared, which is an exponential speed up. And there's much, much more for reasons that I'll now go into. So, let's, why can quantum computers do some serious damage to data analysis problems? Well, let's look at the things that quantum computers are good at. Quantum computers are really good at linear algebra. That's basically what they're good at. Why are quantum computers good at linear algebra? It's because quantum systems, the whole dynamics of quantum systems, as was really brought forward by von Neumann in his famous book, The Mathematical Foundations of Quantum Mechanics, is about vectors on very high dimensional spaces, and the dynamics of the system multiplies those vectors by matrices. So at bottom, the mathematical formulation of quantum mechanics is about linear algebra on very high dimensional spaces. And you could say that look at what's happened in the history of quantum computing over the last couple of decades, which is really the whole history of quantum computing. And you see that it was figured out, back in around 1993, that you could do discrete Fourier transforms, which the fast Fourier transform on a classical computer over n-dimensional vectors takes time n log n, or n log n operations. On a quantum computer, it takes time order log n squared operations. Finding eigenvectors and eigenvalues of n by n matrices. Well, on a classical computer, the best you can do is Gaussian reduction. By the way, who discovered Gaussian reduction? I'm sorry? Turing. Turing discovered Gaussian reduction. I know it was Newton, actually. Newton discovered Gaussian reduction, but it got named after Gauss because Gauss was so famous, so much more famous than Newton. Anyway, on a quantum computer, again, finding eigenvectors and eigenvalues takes time order log n squared. Similarly, matrix inversion, to invert an n by n sparse matrix on a classical computer takes time order n log n using conjugate gradient descent, but on a quantum computer, again, it takes time order log n squared, and database search gets a reduction from n to square root of n for search of an unstructured database. This is kind of interesting because you see these things, these are all matrix operations, and what happens is you simply say these are matrix operations, and by being sneaky and clever, you can take a description of a matrix, pop it into your quantum computer, and then have the multiplication, the time evolution of your quantum system is just multiplication by a bunch of matrices, and if you have the right set of matrices, heck, you can invert matrices, or you can find eigenvectors and eigenvalues. So you get an exponential speed up. But when you have unstructured problems or less structured problems like NP-complete problems, for example, generic hard optimization problems, usually the best that you can do is the square root of n speed up here. So let's take a look at how these things play out. Oh yeah, sorry. So here's the basic idea. In quantum systems, I'm sorry, you know, I was very excited to see other talks that people are giving, because I see that there are other people here who actually use my version of PowerPoint. This is my version of PowerPoint here, right here. PowerPoint I regard as a tool of the devil. It was, you know, made by businessmen to convince other businessmen of things that aren't true. And so it's, of course, very appropriate for scientific use. Anyway, so what happens? Here's the basic idea. So if you have your data, which is a vector in a gigantic dimensional vector space, say n is capital N is 2 to the little n, over complex numbers. Why complex numbers? Well, we get them for free, even though our data is usually in the form of real numbers, or actually binary numbers. Then what we'd like to do is this vector can be mapped into a quantum state, V, right here. This is, you know, these funny bracket notations. If you haven't studied quantum mechanics, this means that whatever the thing in this bracket is quantum mechanical, right? So there are two ways of making things quantum mechanical. One is to take a letter and replace it with a Q. So Google goes to Krugel, right? Which is a project that I worked on with Sergey Brin and Larry Page, Krugel, Quantum Internet Search. But then, of course, Google's Quantum Artificial Intelligence Lab has Google in these funny Dirac brackets. You know, the Krugel, they'll call that first quantization. Google and Dirac brackets is second quantization. So you map it to this vector over a large dimensional vector space, but it's only over small n qubits. So you get an exponential compression in the representation of the data. And then you can do these things like performing quantum Fourier transforms, doing matrix inversions, evaluating overlaps of vectors, et cetera. And you can do this all in polynomial time. And this is the secret to these algorithms. I mean, Scott mentioned one of the secrets, which is you add up a whole bunch of things with positive and negative terms and evaluate the small residue. And then you can do this using kind of generic linear algebra, the things that show up in MATLAB, the BLAS, the basic linear algebra subroutines. Almost all of them are exponentially faster on a quantum computer. So for example, here's one example. I won't go into this too much because I actually don't have time. K-means, this is the example I described before. You're given, you're told that your data sits in 3 clusters. So there are 3 clusters here, but you don't know what the best cluster is. And so what you do is you just pick, 3 of the possible seeds. You assign each vector to the closest seed. You calculate the means. You make the mean the new seed, and you do it again. And this takes time for m vectors and dimensions. Classically, obviously, it takes time at least k mn. You can do it like that. Quantum mechanically, it takes the logarithm of that time to do that. And then given a new vector of data, you can assign it to one of these clusters. This is a classic machine learning algorithm. It's actually called Lloyd's algorithm from Stuart Lloyd, to whom I might be related to in some past universe. I don't know. Okay. Okay, so I said I'm not going to go into it. This is the mechanisms, but you just prepare your vector of data. For this, you need a special purpose device that will map large classical vectors into quantum mechanical vectors. This is called a quantum random access memory, and one of the big open problems, technological problems, of how to build and implement these devices is how to build such a quantum random access memory. I might have time to go into that a little more. Anyway, you just do, you just do a bunch of quantum stuff, and then you get the answer in time logarithmic in the size of the problem. Here's another popular kind of machine learning algorithm. It's called a support vector machine. Now, it took me the longest time to realize that where's the machine in support vector machine? It's actually an algorithm. It's not a machine. But your goal is, given 2 labeled sets of data, so I'm given this bluish cluster, sorry it doesn't show up very well, this reddish cluster, your goal is to construct the maximum margin separating hypersurface. So I want to construct the surface that divides these clusters of data that has the maximum margins. These margins are given by these little yellow things here. And then if I'm given another point, If I want to assign it to one cluster or the other, it shows up there, I say, aha, I'm going to assign it to the red side. If it shows up here, I say, aha, I'm going to assign it to the blue side. And this is a very commonly used machine learning technique. And as you can imagine, you need to solve linear or polynomial equations with equality or inequality constraints. You minimize some quadratic objective function, which could be, for instance, the least squares minimum error function. The classical time, naturally, it can't take time less than polynomial in m times n, but the quantum one takes polynomial time in log mn because you're simply inverting very high-dimensional matrices in order to make this happen. And you can go through this. This is an algorithm constructed with my postdoc Patrick Rebentros, who's from Munich. You can show that, if you can do all the steps, including when given a new vector to assign it to one cluster or the other, in time exponentially faster than you can do classically. All right. So here's another application, minimum error state discrimination. You know, I think I'm going to skip over this because I don't have a lot of time. But you can do some very sneaky tricks with these quantum systems and to essentially turn states of systems into density matrices or quantum states of systems and then do all kinds of fun things with them. Yeah, so here let me go to this topological algorithm because I think this is a fun topic for an audience primarily of mathematicians. Let me describe this, how this algorithm for persistent homology works in a little more detail. This is a well-known technique. It was developed over the last 20 years or so, the classical technique. So how do you actually find this hole here with a classical algorithm? So what you do is you set a length scale, epsilon. You start with epsilon to be very small. And then you connect any 2 points. If you have a space, this is a metric space, so you have a notion of distance between points. You connect any 2 points that are within epsilon of each other. And this gives you a simplicial complex. It's a triangulation of this data. Now, when epsilon is very, very small, everything's disconnected with each other. The thing is all holes, as I mentioned before. When epsilon gets bigger, and here epsilon is sufficiently big that I think if I went around and connected everything, it looks to me like all of these things around this hole would be connected, and so this hole would actually show up in the simplicial complex. Now you map each simplex. The idea is each simplex is just a collection of a number of points. These are 2 simplices, so they have three points, or 2-dimensional simplices. But then I have tetrahedra, which are 3 simplices, and I have 4 simplices, 5 simplices. I have simplices of all dimensions. It's not hard to convince yourself that there are 2 to the n possible simplices if there are n points, because any set of k points could be a simplex. And if I look at the set of all possible subsets of n sets, the power set has 2 to the n members to it. I map each simplex into a quantum state over n qubits. It's perfect, right? Little n qubits gives me 2 to the little n dimensional Hilbert space, vector space. Each simplex gets mapped to a vector in that vector space. And then questions about identifying holes and voids can be asked about questions about looking at a large dimensional linear operator called the boundary map. The boundary map actually is just a linear operator that maps each simplex to its boundary. So for example, this simplex of these 3 things right there, the boundary of the simplex simply gives me a superposition, the sum of this simplex, this one simplex, this simplex, and that simplex. So it's a linear operator, and then the holes and voids at all dimensions correspond to the kernel of this map. And so you simply need to find the eigenvectors and eigenvalues of this boundary map, in particular the eigenvectors with eigenvalue 0. These are the representatives of the homology of this complex. And this is something you can do in time order n. Classically, it takes time order n factorial. It's worse, actually. It's something like 2 to the 3n to find this. You vary epsilon and you repeat, and then you just keep on going, connecting these, and at each scale, you find how many holes, voids there are in this complex. And then if a hole or void persists over many scales, you say it's actually there. Why is this useful? It's because, well, I mean, what is data after all? Data is information that we got by sensing the natural world. We took something that was out there, it was continuous, we turned it into some digitized version. In this process, we mangled and distorted the relationships between the things in the outside world. But, you know, topological features are exactly those that are invariant under continuous distortions of this data. So, topological features are often the things we're interested in the data that we're looking at. This was a point made to me by Michael Friedman again, who gave this wonderful quote, what is topology? Topology is the discrete residue of geometry. Right? I still don't know what it means, but it's a great quote. All right, what other things we can do? Machine learning looks for patterns in big data. Many machine learning algorithms rely on things like Fourier transform, eigenvector and eigenvalue finding, matrix inversion, etc., etc. So quantum machine learning can supply exponential speedups for these problems. Now, I see I have a little more time, so let me actually bring up the kind of open problems. So the first one is this question of a quantum random access memory. How do you take, let me go back to somewhere back here. I'm really terrible at using these kinds of things, right? Because I normally, like many people here, I normally just draw stuff on a blackboard. So let's go back to here. If we have a vector of classical data, it sits in some, you know, CD or something like that. I usually carry around a CD with me. Actually, it's a DVD. It's a DVD that somebody sent me. It's called Is the Bible True? Okay, I don't know because I've actually never looked at this CD, this DVD, but if you imagine, what your goal here is to take billions of bits of information, which, since I don't have it, I can't show it up, but imagine I'm holding up my DVD of Is the Bible True? It's shiny, and it consists of billions of little mirrors to show a 1, or absence of a mirror to show a 0. And the way it normally works is you spin it by a laser, the laser gets focused to a diffraction-limited spot. If the laser bounces off, the mirror, it says, oh, it's a 1. If it doesn't bounce off, it says it's a 0, and you read it out sequentially like that. How could I actually take this classical vector stored on what is actually, you know, a large system consisting of many atoms, and turn it into a quantum state over a small number of systems? Well, actually, turning the information in a CD into a quantum state is not hard. If I have this CD and I take a single photon created by a laser, I put it through a concave lens, the photon's wave packet gets expanded like this. So I have one photon, it gets expanded so this single photon bounces off the entire CD at once. Now, where is the photon? Well, the photon is in a quantum superposition of being in all the modes of the electromagnetic field that correspond to mirrors. So this photon is now in a quantum superposition of all the states that correspond to 1. So this is actually eminently doable. You can actually take classical data and turn it into a quantum state quite easily. The problem is actually turning it into a quantum state over quantum bits that you can then encode in your quantum computer. This is a difficult technical problem. There are my colleagues and I, Vittorio Giovannetti, Lorenzo Marconi, and I have done a proposal for how to do this, but I wouldn't say that our proposal could be realized at the moment. However, it's not necessarily a more difficult technological problem than building a large-scale, fully error-corrected quantum computer, which, as Jay mentioned, is also an extremely difficult technical problem. If you could do this now, then you would, however, be able to do a lot of stuff. So let me just say in general what you can do. So if you just think of all the things you can do by putting together Fourier transforms, finding eigenvectors and eigenvalues, inverting matrices, there are lots of things you can do. For example, one algorithm we've been working on recently, which we call is for doing portfolio management. So with portfolio management, you have a large vector of the historic returns of all the stocks on the stock exchange. This is a large vector. There's a lot of data in that data set. And what you want to do is you want to find the investment now, which will maximize your return either tomorrow, or if it's for retirement, a few years down the road, while minimizing the variance of the return. Or let's say you want to fix the variance and give the maximum return for fixed variance. This is a quadratic optimization problem. It can be done exponentially faster on a quantum computer. And then we have an algorithm for doing quantum portfolio management. I was actually telling Madhu Sudan earlier that when we did this, it's important when you call anything quantum, you have to Google it to see if somebody's used it. So I Googled quantum portfolio management, and I found there's a company in Great Britain called Quantum Portfolio Management. Similarly, we also quantized the Netflix algorithm. It turns out that you can find principal components of data just by finding eigenvectors and eigenvalues. It's exponentially faster on a quantum computer than on a classical computer. And then you can do principal component analysis on people's movie preferences and recommend movies to them. So we said, that's great. We'll write a paper called the Quantum Netflix Algorithm. It's just a matrix completion algorithm. So I Googled quantum Netflix algorithm. It turns out that Netflix calls their own algorithm the quantum algorithm. What are you going to do about that? So I understand from Hartmut Neven at Google that Hartmut has an agreement with Sergey Brin that nobody else at Google is allowed to use the word quantum in their name and to take the word quantum in vain, which is a good thing. Probably at IBM they have a similar rule. What is this interesting for? So I have 2 minutes more, and maybe I will actually try to talk about, what I was supposed to talk about, quantum computing in society and the universe. The first thing is, if we can solve certain technological problems, those of building relatively small-scale quantum computers, which would be excellent for doing this kind of quantum machine learning problem, then we might be able to solve some difficult and we've solved the problem of getting classical data into a quantum state. Then we might be able to solve some societally very useful problems. For instance, consider another database, which is the database of all the genomes of all the human beings in the world, a database that does not yet exist. It would be a very interesting database, however, to analyze it. If there soon to be about 10 billion human beings, each genome is about 10 billion bits, it's 10 to the 20 bits in this database. You'd like to be able to look for clusters in this database. You'd like to be able to look for topological features of this database. And you could actually do this with such a small quantum computer. Moreover, actually, because these quantum states, you're doing it by only a very small number of calls to the database, it actually has a feature of security that if you make a call, you can find out, for instance, topological features of this database without actually ever knowing, you won't know almost nothing about anybody's individual genome, which would be kind of nice, because speaking as an American, I would really not like my insurance company to know my genome. That would be, in the United States, we don't have laws about this kind of thing. So let me finally talk about, in the last few seconds here, about deep learning. Why work on deep quantum learning? Well, first of all, it sounds cool. Right. So again, I've been working on this quantum machine learning ideas for about five or 6 years now. They were suggested to me by my postdoc, Patrick Rebentrost. He came and said, one day he said, let's look at deep learning. And I said, well, what's deep learning? And at first I thought, oh my goodness, this is going to be great. Deep learning, computers are going to tell us about, life and truth and happiness and love and all these deep things. Very sadly, I learned rapidly that it's just, it's a deep neural network with many, many, many layers. Which nonetheless can do very great things. I mean, deep learning networks have been shown to be excellent at recognizing pictures of kittens on the internet, for example. You can train them by vast data sets to recognize pictures of kittens. Though actually, just from a Bayesian perspective, if somebody gives me a picture from the internet without even opening my eyes, if I guess it's a kitten, right, the prior probability is very high that it is so I can actually do a pretty good job without any learning whatsoever. So why do deep quantum learning? Well, first of all, it sounds cool to have it called deep quantum learning. But the other reason is, I think, these unsolved questions about computational complexity and pattern recognition. So as Scott pointed out, and Scott has done some, and his collaborators done wonderful work over the last decade about these ideas of quantum supremacy, showing that you can take rather simple circuits, including linear optical quantum circuits, which are much, much easier to build than large-scale quantum computers, and that these can generate patterns that cannot be generated classically. And there's a lovely apparatus of proofs relating to the polynomial hierarchy that Scott alluded to that show you that it seems very unlikely that classical systems can generate these. But now let me raise as an open question, can quantum systems also recognize these patterns? So the kind of shallow quantum circuits that Scott was looking at, you could actually, they generate statistics, which under certain assumptions can't be generated classically. But suppose somebody just gives you this statistics. Can I come back and say, oh, that was generated by this circuit? Moreover, I can now that I have this circuit, I can generate other statistics according to this, and I can recognize patterns like this. We don't know the answer to that. So the complementary to the question of sampling, that is, can you generate patterns that can't be generated classically, we have this other question, can quantum systems recognize patterns that can't be recognized classically? So let me just close, since I'm out of time. Let me just say that quantum computers are, I've been here probably, I think I'm the person of this group who's been working on quantum computers for the longest, back in the days since the 80s when nobody was interested in it at all, which is, as I mentioned, why I'm a professor of mechanical engineering, because it turns out that mechanical engineers, if you say, we're going to build a quantum computer, they say, cool. Whereas back in 1990, 1993, if you told physicists, you said, we're going to build a quantum computer, they say it's theoretically impossible. So it is not theoretically impossible. It's practically possible to build all kinds of quantum devices, and we're at an extremely exciting time where the kinds of devices that people at IBM, Google, Microsoft, and other places, including private companies, startup companies, are building, can start to do things that you can't possibly do classically. And now we have to see can we get them to do things that are useful and interesting for society? And that's an open question. So I'll stop there. Thank you very much.
Okay, I think we're ready to kick off part 2 of the hot topic. We decided it would make sense to reverse the order of the next 2 speakers. So the first speaker this afternoon is going to be Chris Monroe, who is a professor of physics at the University of Maryland and co-founder and chief scientist at, hey, this is what Seth was talking about. You put a Q in there, IonQ Inc. And he's a leading researcher in the use of individual atoms for realizing quantum computation and quantum simulation. And the title of his talk is Reconfigurable and Scalable Quantum Computing with Atoms.
Thank you, Philip, for the invitation. It's certainly a delight to be here for this very esteemed audience. I guess we're going to hear this afternoon more on the experimental side of things, and I thought I would start by reminding you of what I consider to be the 2 rules of quantum mechanics. And although this is the way we generally interpret quantum mechanics, it does help you think about how to design an experiment. So this is probably a review for most of you. You know that quantum mechanics is a wave theory. There's the Schrödinger wave equation. And when we reduce a quantum system to a single bit, a quantum bit, it can be in a superposition of both 0 and 1, with A and B are the weights of the superposition, the amplitudes, and A and B follow this wave equation given by the energy function or the Hamiltonian. Okay, so this by itself is not very revolutionary. It's just a wave equation. But of course, the conceptual leap in quantum physics is that we have another rule that says that first rule only works when you're not looking. And it's a little goofy to say it that way, but when you consider what it means to look, it doesn't mean there's a conscious being measuring something. It just means that your system is so well isolated that the environment doesn't interact with it. Because if the environment does interact with it, you have to treat the environment as a quantum system as well. It becomes entangled, and sooner, before you know it, the entire universe is involved, and we just can't deal with that with so many numbers of degrees of freedom. Of course, this rule number 2 has all kinds of problems in that it seems that when we measure something, we affect it just by measuring. We also have probabilities that are part of it, part of the second rule. This is, as an experimentalist, I'm sort of agnostic as to the philosophy behind this, but I do realize that in the laboratory we have to be able to apply rule number 1 without rule number 2, and then we want to apply rule number 2 while getting all the information out as we can. So obviously, to build a quantum computer in the laboratory, we need quantum bits that are quite exotic. They're so well isolated that they can be in a situation where they do not get measured. These are called pure quantum systems, and nothing is 100% pure, and there's always a little bit of a leak from the environment, and of course our job is to minimize that leak, but then turn on the leak on full blast when we measure the system. So just the ability to be able to measure a system strongly and gate it on and off makes laboratory quantum computing very, very difficult, of course. And so today we'll hear what I would say are 2 of the top candidates to build a quantum computer right now, and I'm going to talk about individual atoms. So, in fact, the atoms are charged. They're atomic ions, and you might not see them here. It's actually, I can see them on my screen. You can't see them up there. This is an ion trap. It's a hunk of silicon that's plated with gold, and you can't see up here in that bow tie section, there are about 96 electrodes on this surface, and there's a hole, a little notched. But if you can see maybe these dots, I of course drew them in. They're real images of individual atoms, but if I blow that up, it looks like this. Each dot you see is an individual atom, atomic ion, and of course they repel each other due to their Coulomb repulsion, and that is they form an equilibrium crystal that's a compromise between the repulsion and the external confinement. So we're actually applying forces in all 3 dimensions to maintain this crystal of individual atoms. I wouldn't call it a solid, but these crystals can last for hours or days, so you could call it a solid if you want. It's atomically perfect because every atom here is the same element and the same isotope. In this case, well, I might not even talk about it. It does matter as long as you know what you're doing. These are ytterbium ions, isotope 171. Okay. So their spacing is several microns, which you can optically resolve. And the reason you can see them is that we shine laser beams to hit the atoms, and they fluoresce, and we capture the image on a very sensitive camera imager. Okay, so this is the platform that we consider building a quantum computer out of, and the benefits of using individual atoms is that they're, in a sense, they're God-given qubits. They're atomic clocks. Every one of those atoms is identical to a part in 10 to the 10 very easily. If we wanted a part in 10 to the 15, we could do that. We don't need to do that, fortunately. So in a sense, if you can somehow trap lots and lots of these atoms, they're perfectly replicable. The qubits, when left alone, are perfect. You can't get any better. Now, of course, you need to control them, and this is where all the work goes in making an atomic scale quantum computer. So, given these are atomic clocks, we can take advantage of internal states in the atom to store our quantum bit. These could be electronic orbitals. More typically, they're spins, the direction of spins of an electron in the atom. It doesn't matter so much that there are many candidate qubits inside of an atom, and we can measure the qubits by shining another laser beam such that one of the 2 quantum states fluoresces, it's bright, and the other one is dark, so bright, dark. In this image here, they were all in the state they were all in a particular state that fluoresces. Of course, if they're all in the other state, it's a boring image because you don't see anything, it's all dark. But it's a very direct measure, 1 and 0, bright, dark. Okay. So I want to go through some of the recipes on how we actually build quantum gates out of these atoms. Because they're ions, they couple very strongly with one another, but not the inner workings of the atom. The qubits inside the atom, even though the atoms are only a few microns apart, That's miles apart atomically speaking, so the individual qubits don't interact directly. However, their motion interacts very strongly, and it's very physical what's going on here. It's very mechanical. If you wiggle one of these atoms in space by applying a force, you send sound waves through the chain, and you can use that to mediate entanglement and make quantum gates. There are many approaches to doing this, and they all work roughly the same way. We can shine laser beams on select qubits that we would like to entangle. And this laser beam applies a force. It's an interesting force because the direction of the force depends on the state of the qubit. So as I've drawn it here, if the qubit is in the state 1, let's say it goes up. If it's in the state 0, it goes down. So in fact, each atom here is in a superposition of 2 places in general. Okay? And these places can be optically resolved even. Okay? And when you do this to 2 ions, or any 2 ions, their Coulomb interaction is modulated, and you can use that to basically derive a quantum gate. You can make entanglement that way. This is the workhorse of making quantum gates with individual atoms. You can see a problem right away. If I put too many atoms in here, the motion gets very complicated, and that's true. And I'll return to that point in a minute. I don't think we're going to do this with thousands of atoms in one line. Maybe 100, but not much more than that. Okay? So once the laser is shined in the right way, we can have atoms entangled that way. And so a quantum computer program would be a bunch of lasers that are pulsed on and off on given pairs of ions and given single ions to do single qubit gates. Now, this is a schematic of an apparatus that we've recently used with only 5 qubits, so anything it does is going to be trivial. But what's interesting and what's very hard here is not the perfect qubits. That's actually easy. It's the controller that we institute around these qubits. And in this case, we have laser beams coming from both sides, but these laser beams are the special ones that turn on and off. We have 1 laser beam per atom. Okay? So there is some overhead in applying those classical control fields on the atoms. But the good news is that we can do a gate between any pair of these atoms. One way to say this is that the graph connecting the qubit is fully connected. With 5 qubits, there are 10 possible pairs, and we can derive a gate between any of those pairs. And so there's a certain speed up associated with that. The connectivity graph makes it easier to do certain algorithms. Now, in this setup, what I find interesting, and this is also echoed in Jay's talk, and also John will talk about, the idea of having qubits that are programmable, that we can start to think about applying software, tools, architectural techniques to design the system. And so I like to call this, we call this the quantum stack, where at the top level of the stack you have the user that doesn't want to know what's at the bottom of the stack. When you use your iPhone, you don't know what's inside. You don't want to, and you don't care. You just want to use it according to certain rules. So the user has some algorithm they'll want to do, some application, and they might look in a textbook and find the gates that they want to apply. These might be controlled NOT gates, Hadamards, and so forth. Now, in these ion traps, in fact, our native gate is not a controlled NOT gate. The native 2-qubit gate, we call it an icing gate. It's sort of how 2 magnets interact via their direction of spin along a particular axis. And there's an interesting step here to go between high-level textbook gates and the gates that we have in the lab. There's a compiling step. And there's a black art in quantum computer science on how to compile gates efficiently to reduce gate counts and so forth, and it's a very active field right now. And I'm happy to say that a lot of the quantum computer scientists are digging down into the stack to investigate the real hardware we have in the native gates in the laboratory. And down there's another step. We have these icing gates. To make them, we have to do pretty complicated laser pulse shapes, as I sort of glossed over to make those gates. And then finally, we have the quantum hardware of individually optically addressing atoms and performing the computation and making readouts of the quantum states. Okay. So I think any quantum computing architecture now, at least in a few technologies, we're starting to think of this entire stack. And a gain on any one of these levels of the stack is really important. It's not all down here. It's also gate compilation and qubit assignment and so forth. And the qubits are all a little different. The controls are a little different. And propagating noise, you can take advantage of that by smartly ordering gates in certain ways. So this again, it's a very interesting field now, and I'm glad to see that lots of folks in quantum computer science are starting to pay attention. They're digging deep. So here's an example algorithm that we might apply. This is, I won't get into too much detail, this is a so-called oracle algorithm, one of the well-known but useless oracle algorithms in quantum. It says if you're given a black box function here, it's an n-bit to 1-bit function, modulo 2 here, and it has a hidden, it has a hidden string here, C. The question is, what is that string C if I'm given the black box of the function? How many queries do we need of the function to find out what C is? Well, classically, you have to evaluate each bit of C to get it out, so you need n queries. But quantum mechanically, because you can process superpositions on the inputs, you only need one query. And this is an example circuit with a 4-qubit Bernstein-Vazirani algorithm. The 5th qubit is just a workspace in Ancilla, and this is data from our 5-qubit ion trap. And what I have plotted here are the probabilities on the vertical axis, the oracle that we programmed all 16 4-bit strings C, and this is what we detected. Kind of a boring plot. If it were perfect, there would be a 1 on the diagonal, and everything else would be 0. And our gates, by the way, our gates are about 98, 99% per gate, which is okay. I think we need to do a lot better than that. And when you do several gates, the errors tend to be in the low 90% as expected. Now, as Jay mentioned, IBM coincidentally, or I should say maybe our ion trap lab coincidentally has 5 qubits. And coincidentally, the gate quality in both laboratories is about 98%. So we also ran their quantum experience, and there's Jay and his colleague Jerry Chow. They gave us super user status. They gave us permission to do this, and we ran the same algorithm on their system, and roughly got the same results. You know, decent, respectable probabilities here. The one thing that's different here is the connectivity of the qubits. In their superconducting system of only 5 qubits, the connectivity was nearest neighbor with a central hub. And again, in this geometry, they're thinking of tiling a two-dimensional grid, but they can, of course, make connections, more connections if they want, when they add, if they wanted to. But the original system had this connectivity. But when you look at the circuit, you don't really need much connectivity in that circuit. Clearly, bit 5 is going to be the center one, right? Even I can recognize that compiling choice. You would assign bit 5 to be the center, and you should be able to efficiently do that circuit. Well, another algorithm that's a little more complicated, this is a similar oracle algorithm. It's called the hidden shift algorithm. 2 functions are the same except the inputs are shifted. Find that shift. Turns out you need exponentially many queries classically to find what that hidden shift is. And again, quantum mechanically, you do it with 1 query. I won't get into the details, but this is an example circuit for 4. Here's again the results in the ion trap. But now you see the less connected superconducting system doesn't perform as well. And it's because the connectivity isn't matched to the circuit very well. So, you know, what we learn here is that, you know, maybe it's obvious. Match your connectivity to the circuit and the other way around. Find the algorithm that best works with your native connectivity. Okay? So it just demonstrates we're starting to think about architectural issues in quantum computers, which is very fun. And we can even compare. A computer doesn't necessarily care what's inside. A computer has rules, and it works regardless of the hardware. And so this is just a verification of that idea. Now, in slightly different vein, these trapped ions, we can store lots of them. And there's a little bit of a trade-off. If you have a lot of them, it's harder to get control over the individual ones. So we do other experiments with ions by having less individual control and more global control. In this case, we have an all-on-all icing model. It's almost like we're applying simultaneous gates between all pairs. And this icing interaction is a long-distance one. It has a long range. It falls off roughly with 1 over distance. And we can have a transverse field. This is a famous transverse icing model. It's the simplest model that admits a quantum phase transition, actually. And with lots and lots of qubits, we can do such a quench experiment by preparing all the spins along X and turning on this Hamiltonian. There's a competition between the spins wanting to order according to that and them being polarized along a transverse magnetic field. And I won't get into too many details, but this is 53 ions. We initially prepare them all in one state, You'll notice they're not equally spaced. That's just bookkeeping. It's not, we know how to make them equally spaced if we have to. And what we're going to measure in our order parameters, the length of the domains that are formed. Now, when the domain length is smaller, that means we're starting to see domain walls, and we're seeing this competition between the two. And again, I won't get into too many details, but just to point out here that the mean size of the domain versus this ratio of the field divided by the Ising coupling, we see this sharp kink, which is indicative of a phase transition. This is called a dynamical phase transition. It's more of a physics result than a quantum computing result. But it's impossible to calculate this curve. This is just two lines that are fit to the data heuristically. But because this has so many qubits, we can't really calculate what's going on here. So anyway, I think in the long run, we of course hope to deal with lots of ions and have the control that we showed with just a few qubits. And part of the bad news here is that 50 qubit experiment, this is actually the lab next door to it that does something else, but it looks similar to this. And this is everybody's nightmare. I hate to say in my field, in atomic physics, people put pictures up like this, and they're very proud of themselves. They were able to deal with all this equipment and cables. I'm horribly embarrassed by this because this is just no way to scale. But the good news is, well, this is a university lab. We don't do engineering at universities. In fact, I would say nobody does engineering at universities. But we're needing now to do engineering in this system. These controllers have to be engineered top down. And you know, that last picture should remind you, I think somebody showed this picture this morning. I think Jay showed the picture of one of the early vacuum tube computers. You know, this is an unwieldy system, many thousands of vacuum tubes, and it looks a little like that, a lot of cables. This probably looks worse. But I'm happy to say that we're actually very far along on a design that combines lots of ions with individual control. And this basically is a template for most of the work here is the laser beams. There's 32 laser beams individually controlled. They're diffraction limited spots. And they actually go in, it's a little hard to see. This is a vacuum chamber that holds the individual atoms. There's a chip trap in there. I showed you that picture before. This whole thing occupies about a cubic meter. And you can see the controller behind it. I think you can see a couple of computers there and a bank of electronics. But this is, I mean, I just know it's going to behave better than anything we've done before because it's been top-down designed with this in mind. And this is the master laser, which is an industrial laser. It only has one adjustment, and that's the on button. So we need devices like this to go to the next level. I mean, I'm comfortable working on lasers. I've done it all my life, but I'm really happy not to because we need to move on. The laser is a tool. It's our controller. We have to now start to think about building bigger and bigger quantum circuits like this. By the way, these blue cables, there's 32 of them. They're not hooked up yet, but they hook up to an optical controller that will have an RF signal on each individual controller beam. Okay. So I mentioned that engineering doesn't happen on campuses. This is on campus, but this blueprint is being copied at a startup company called IonQ. And this is not something I anticipated many years ago, but we're really at the limits of what we can do at a university with this technology, and nobody has yet tried to engineer atomic physics to this level. So it's something that needs an industrial approach where we can have real professional engineers, not just physicists like me, but also software, algorithm people, and hardware people to deal with the control of that system. So again, IonQ's mission is to build a small-scale quantum computer. And the nice thing about these atomic ions is that their connections are not only fully connected over a small number, maybe 30 or 40 qubits, the connections are reconfigurable. These atoms are not wired. There are no wires. The wires are from the outside. They're laser beams, and we can change that on the fly. If an algorithm comes along that demands a certain connectivity, it's a software problem for us. We use the same hardware, the same qubits, the same atoms. Okay, so that's sort of the vision here. Now, this plot is an interesting one. I think we'll see lots more plots like this in the future. It shows on the y-axis the number of qubits, which taken by itself means nothing. I can give you 1,000,000 qubits. That's easy. I won't give you much control of them and very little entanglement. That's not useful. And the x-axis is the effective number of gates, and it's related to the error per gate. This is roughly 1 over the error per gate, if you want to think of it that way. If you have 100 gates, you probably had 1% error or something like that per gate. Now, that's a little, I put effective in there to leave wiggle room there. But this horizontal line is where classically available simulation tools exist. So if you only have 40 or so qubits, we can actually simulate that classically. Not 50 or 60, probably, I'm not sure 60 will ever happen, but, so we need to be north of 50. That's why you hear that number 50 a lot. Now up here, when we get above 50, there are some interesting applications, perhaps even new algorithms. The Shor's factoring algorithm unfortunately has a very steep scaling here. Somebody talking about approximate optimization routines that are maybe less interesting, but this is where we all want to be, up and to the right. Lots of qubits, lots of gates. And the ion trap community is sort of all around the map. There are some experiments that have 99.9% gates, but only on 2 qubits. The key is extending that to lots of qubits, and that's a big challenge. Other experiments, including this 53 ion experiment I showed here, they have less control and decent effective gate counts, but less control. And so it's only the solid points I want to mention. And conveniently, these 2 points haven't yet been realized, but we look forward to the next year or two where they will be, hopefully crossing that line pretty soon. Okay. So a little bit, this is a little bit of a controversial curve. I thought I'd put it up because it's kind of fun. Qubit Economics. Now, what's interesting is that you can't just add qubits and hope that everything will just work great. When you make a quantum system big, in general, it becomes classical. So what we're calling on here is a quantum computer to almost get classical, but keep its quantum coherence. And every technology will have its own curve here, but I'm plotting the cost per qubit versus the number of qubits. I start with 2, because 1 is sort of trivial. 2 is the smallest number of qubits that you can have entanglement. And I would argue that a curve probably looks something like this. Maybe it doesn't bend exactly like that, but there's going to be a steep cost initially just to get going. I think there's going to be a sweet spot. If you can do 46 qubits, you can probably do 47 without much extra cost. But there's going to be a brick wall at some point. And there's interesting physics behind that brick wall depending on the technology. And the technology, in atomic technology, I'm guessing this is going to, for us, be somewhere between 50 and 200 where that wall is. And it's going to be based on dealing with all this complicated motion. And what's interesting here is if you plot constant dollars now, these are hyperbolas, right? Cost per qubit. So you can clearly see, I mean, it's sort of obvious, you're not going to want to go too much beyond that wall because you're going to be having to spend a lot of money to do that. So what this implies is that we need to think of an architecture, if you believe that things will get hard at some level, we need to think of an architecture that's modular. And I would point out that almost everything that has complexity in this world is modular. We don't build the next generation silicon classical computers by just making the chip bigger. We make multi-core computers. Airlines don't fly between every pair of cities. They have hubs. So there's just a natural modularity in these systems. And with ions, I didn't talk about it much at all. Scott actually mentioned it. The idea of using photons to generate entanglement. Now, these atomic ions that are optically active, we can actually entangle an individual ion with a photon. And if we send these photons between different modules on a bunch of beam splitters and detectors and so forth, we can actually entangle individual atoms that are remotely located. And so you can see this big architecture. Obviously, this is a PowerPoint quantum computer, but this architecture, each red box might have 50 local ions that are fully connected, and maybe a few of them are communication ions that send photons off to other systems to keep the scaling going. Now, we pay a big price because the connectivity is being broken in a major way. We have this densely connected system here, densely connected system here, and then just one little spaghetti fiber going from A to B. But, well, if that's the only way to scale, that's the way we're going to have to do it. This is actually using these photonics. This is obviously a university once again. Here we have, in this experiment, we had exactly 2 atoms about 1 meter apart. And we use this photonic interface behind the black curtain there to teleport a state from 1 qubit right here to another qubit over here. Now, teleportation might sound like an unfortunate term because we're not going to be using it to teleport cells or certainly bodies. But for an individual qubit, teleportation is a great way to move information around. And in this case, what we did, we had an unknown qubit. Of course, we knew what it was. We uploaded it. And through the entanglement given by these photons, we were able to recover that same qubit over here without measuring it. Of course, we measured it, but we provide many different types of qubits and verify that it works. And it works okay. It's slow. It's right now the world record in doing this kind of interface is about 10 hertz. So nobody wants a computer at 10 hertz, I guess. Maybe a quantum computer. It has other speed-ups inherent to it. But again, this is still a little researchy, the photonic link, but in the long run, it's going to have to play a part if we hope to scale to thousands or millions of qubits. So I think I'll conclude here and just note, maybe advertise for John here and also what Jay spoke earlier. It's a really exciting time now, basically because of these two technologies. They're ready to be built. And this is evidenced by the large investments by non-government agencies, companies. And that's a big deal because, again, this is where engineering happens. And I think both of these platforms, they're complementary in so many ways that I have to believe they're going to find different applications. And we're going to learn, both communities will learn from each other. So, again, I think that's all I have. Thanks for your attention.
Thanks very much, Chris. Well, as Chris said, the trajectory really of this forum, of this hot topic session is going from ideas and theory vaguely towards actually building this stuff, and that's certainly one way of doing it. And we're going to hear now from John Martinez about another way. John is professor of physics at the University of California at Santa Barbara and research scientist at Google's Quantum AI laboratory, where he's in charge of the quantum hardware team, whose goal it is to build a useful quantum computer. And his title is Quantum Hardware at Google, Progress Towards Exponentially Growing Computational Complexity.
Great. It's a pleasure to be here. I especially like this meeting where you're combining lots of fundamental ideas in, say, mathematics with practical ideas in computer science to actually run and use real algorithms. And I would say it's a particularly interesting time in quantum computing because we're trying to do that. You heard some nice fundamental ideas, and then we're also building real hardware and trying to do something both powerful and eventually useful. And it's my pleasure to talk to you about that today. The field has made huge progress in the last 10, 15 years, and as it's been talked about, there's a large number of companies now even involved in this. I'm going to say we feel optimistic we can make a lot of progress, but it's not 100% sure that we can build this big quantum computer that we actually want to do. It's a hard job to do this. Okay, it's not guaranteed. Certainly we've gone far enough that we should be doing this. So why is it hard? We're dealing with quantum states with tiny amounts of energy where noise can disturb it. There's lots of system engineering issues you have to deal with. And probably the biggest thing in terms of doing something useful is if we're going to build a quantum computer, what we have to do is build something to compete against this guy, which is some big data center or some supercomputer. And, we have a long ways to go to do something like that. So I want to talk today about maybe not doing something useful, but doing something powerful to kind of show that the quantum computer can be eventually powerful and useful in talking about quantum supremacy. Now, the nice thing about thinking about quantum computing is you have some fundamental physics behind you to think that you might be able to make a powerful device. And to explain that, and I'll go over this quickly, I think people have covered that, is that instead of storing states as 0 or a 1, it can be 0 and 1 at the same time in a fully coherent way that you can manipulate those two states at the same time with your quantum computer, giving you a parallel computer. Okay, it's a factor of 2, maybe not a big deal, but you can still do that. Of course, what becomes interesting is when you have more qubits. So for example, two qubits, you're now parallel processing 4 states at the same time, and you've doubled the parallel processing power, if you like it, by adding the qubit. So you can just keep adding qubits, and if you can keep doing this, you're doing an exponential scaling of the power, so that by the time you have 50 qubits, 2 to the 50 is a number about the size of a supercomputing memory. So certainly you're doing something very powerful. If you had 300 qubits, 2 to the 300 is more states than there are atoms in the universe. Clearly that would be something amazing and powerful. And my particular goal is n equal 333. And that's because the Hilbert space in that case is 10 to 100, or a Google size, which clearly is very important for me to want to do that. Okay, qubit systems, we talked very nicely about encoding your qubits in atoms, very natural quantum mechanical system. You take a hydrogen atom, here's kind of a picture of what the wave function clouds look like. You can store a 0 into the ground state and a 1 into the first excited state, which is actually a long-lived state. Put on microwave pulses and see transitions and the like. This is very natural, but it's kind of hard when you scale up in the sense of, let's say, making molecules in this case. And the problem is if you want to have this as a qubit and this atom as a qubit, they're only a few angstroms apart. And if you're going to try to manipulate them with, say, light, the light is very much bigger than this molecule. So how do you selectively, do something to this qubit and not to the neighboring one? And the way you get around this is very nicely illustrated by the ion traps, is you make your atoms bigger. In the case of atoms, you put it in some trap and you move them apart about a micron so that you can use optics for it. In the case of superconducting qubits, we make an integrated circuit, in this case out of superconductors, and we make this quantum circuit atom. Okay, in this case, the white here is just aluminum metal, deposited in the standard way. The dark is a cut in the metal, so there's a capacitance between this cross structure and the ground. And then there's something called a Josephson junction down here that's more or less, it's just a nonlinear inductor. And you form a 6 gigahertz microwave oscillator to generate your state, just like you had a light frequency oscillator here. You just do it down at microwaves. And the quantum mechanics, and this is amazing. This is not at all obvious. For you know that atoms and nuclei obey quantum mechanics, but here we have a huge electrical circuits with 10 to the 20 electrons in it. And the collective motion of those electrons, say the current flowing up and down here, obeys quantum mechanics. Okay, it's not obvious that it would do that, but it does. And you can write a wave function where the current is going up and down at the same time, same way that the electron is on one side or the other at the same time. And given that this is large, we can bring wires in and control it and maybe build some more electronics, and we can technologically engineer this to build a complicated system in the same way that you would, build a transistor circuit. Okay? Just to give you an idea how this works, what we do is we just let it relax to the ground state. It naturally does that. We then put on a pulse of microwaves resonant with the transition, and this makes a transition between the ground state and the first state and back into the ground state. So we do logic on the single qubit, and then after some time we measure it. And then when you measure it, you get a 0 or 1. So what we plot here is doing the experiment about 1,000 times or so to get the probability of a 0 or 1 versus the time in which we pulse up the microwaves. When the time is 0, this curve goes up to here and it's 100% in the 0 state which is what we do. And you note that if we put these microwaves on for about 40 nanoseconds, it goes into the 1 state, because it's 0% probability in 0, 100% in the 1 state, okay? What is that called when you want 0 to 1? That's a NOT gate. So it's a totally classical, with 40 nanoseconds, you made a totally normal classical gate that you know all about. If you do another 40 nanosecond pulse, you get up here, and now you're in the 0 state again, and that makes sense. A NOT gate and a second NOT gate is equal to the identity. Again, that's just Boolean logic. So if you do this properly, you see the whole Boolean logic repeating itself up and down again. But of course, what's interesting here is we can pulse it not for 40 nanoseconds, but for 20 nanoseconds. And now it's 50% 0 and 1. And this is, in fact, when you do it carefully, that's the 0 plus 1 state I was talking about. Now, if you pulse it for 20 and you pulse it for another 20, you get back to the NOT. So this 20 nanosecond pulse, you would mathematically describe as a square root of NOT gate. Okay, classically, you have no idea what that means, right? But it turns out that the mathematics of all this gives you a consistent mathematical description in terms of that, at least in there's more quantum language you could talk about that, but you can certainly talk about it that way. And you see, since it's continuous, you could have any power that you want there as you want. You can make some arbitrary gate, okay? And you see that this oscillates back and forth in a nice way. It decays a little bit here and here, so it's not perfect, but we can basically do about 1,000 operations here before we lose the memory of the device, and that allows us to do algorithms. Okay, so here's a 9-qubit device. These are I's instead of X's now. And then you have little currents here flow through these loops. This is essentially a mutual inductance coupling of that. And that allows these 2 qubits to talk to each other. So we have our control lines down here, both for individual qubits and coupling them together. Qubits reading out up here. And we can make a device. We make 1 qubit. When it's working, we just step and repeat on the mask and go in the clean room and make a bigger system in the way that you make integrated circuits. This is just a picture of the latest device that we're making here. This is 11 by an 11 here, so that's 22 qubits. This is the chip that we make the qubits on at UC Santa Barbara with our special clean room magic to make them work as well as they can. There are little indium bumps right here, and then here there's a carrier wafer, so that connects wires into here, brings it out to the side. And this is made in a foundry so that it's made with very few errors, a very clean environment. And when they're put together, they're put on a circuit board, wire bumped, and then a bunch of connectors go out to the outside. And this we can scale up to, we think, a pretty large number by using that. We put it in a dilution refrigerator that gets to about 10 millikelvin, 1/100th of a Kelvin. Okay, you just buy that. It sounds kind of hard, but you just buy that. And then what happens is the energy, thermal energy at a 10 millikelvin is way, way smaller than the quantum energy of the states, and thus you can more or less ignore the thermal energy. You then wire this up in the terms of normal electronics with filters and whatever, going up to room temperature. So here are the wires that are going up here. We just, mass produce that and buy it. And then here, all the wires that's going down to a crate. And this crate electronics we have here, about this size, controls about 20 qubits or so. And this can be scaled up more and more as we want to go to bigger systems. This is just think about high energy physics and what they do there. And this is our dilution refrigerator, and all the wires that go to the electronics. And then most of the time you're sitting here behind the computer programming the code to get everything to work okay. I like this picture. It's of course a staged picture, and you can tell because the lab is so tidy. It's normally not that nice. Okay, let's talk about quantum supremacy. Here we have all these beautiful theory and experiments trying to make a quantum computer. There's billions of dollars of research going into it. It's all based on the assumption that as we make more and more qubits, we're going to have more and more power, exponentially growing power. Is this really true? Okay, we're going to spend all this money. We want to make sure that that's true. Okay, we want to test it. We assume it's going to be true, and we assume that if it goes wrong, it's because we're putting too much noise in the system or something. But we want to check that. Okay, we want to check it as soon as possible. So that's one way to think about this supremacy experiment. We're going to do a 45, 50 qubit experiment. We're going to take some data with it, and we're going to check whether this thing is working right, and if we have a 2 to the 49 Hilbert space, by comparing the output of that with the supercomputer. Okay, so that's the basic idea. So I'm going to show you the algorithm, and given the crowd here is mathematics and computer science oriented, it's not too hard to understand. Basically, what we're going to do is have this circuit, which I think we've shown before. It has a number of qubits, and we're doing various operations versus time. These boxes here start off in the known ground state. These boxes come from a set of single qubit operations, like the NOT and square root of NOT I was showing you before. And we're randomly choosing these states, but we know what logic gate it is. And then we're going to connect them together via something we call a control Z, but it's more or less looks like an exclusive OR gate of classical logic, more or less the same logic at that. And then we just do it over and over again. And given that we're randomly choosing these, we're going to get an output that's essentially all scrambled. And we're going to run the quantum computer, measure it. There's 2 to the n possible outcomes of 000, 001, 010, 011, etc. And we're going to measure all of those possible states. There's 2 to the n possible states. And we have no information about what's going on here. It's a randomly chosen circuit. So the only guess you can make is that any output k has a classical probability of 1 over the number of states. Okay? But quantum mechanically, that's not what you see. You see some states are more likely than others. So to illustrate that, if I can turn off the lights now, I want to show a little laser pointer. Where did I put that? Oh, here it is. Okay. Now, is that going to, can't turn off the lights. Ah, there you go. So here's a fairly powerful laser pointer with a diffused glass, ground glass. The light is going through that, and then what we're doing is we're getting, yeah, very nice, some laser light coming out here. And I hope people can see at the end, although it kind of looks like a uniform diffuse background, in fact, in certain directions the light is brighter, and certain directions the light is dim. Okay, you can turn the lights on right now. This is something that's well known in physics, and it's called speckle. And what happens is that you have coherent light, laser light, that's coming through the ground glass, and sometimes the light comes through, and it's going in the same way, and it's constructively interfering, giving you something bright, and in some directions, it's destructively interfering and giving you something dim. Okay, and that's why there are bright lights and dim lights. What we're doing in this quantum algorithm is 2 things. One is that you can actually look for speckle itself, and then when you speckle, you know something had to be coherent, okay? But more importantly, what you do is you look at the directions where it's bright and directions where it's dim. You measure that, and then you compare that to what you computed by knowing what this ground glass is doing on the laser pointer, and you see if it matches up. Okay, so that's the basic idea. In fact, we do that by first calculating what this should be, knowing all these states, and the probability is given by the Schrödinger equation, and say you store that in a lookup table, and then you do a correlation. Where was it bright? Where was it high probability? Is that where you predicted it? And the way you do that is you just take the measured value of k's, and for that state, you look up the probability to be that you computed. And since the higher probabilities, the brighter things are going to be more likely, you're more likely getting p's that are greater than p classical, And this cross entropy will be bigger than if you chose it randomly. In fact, the difference between classical, where it's totally random and totally flat, and when you get the speckle is a difference of 1, and you can tell the difference. So you check for that, and then of course you can try it again, and then it takes you about a second to take data and about a day or hours or days to look this up, and then you can check it over and over and keep on making sure your quantum computer is working until you quickly run out of money, and you can't do that anymore. Okay, so let's talk about how it works in more mathematical detail, at least for a physicist. What happens is when you look at these wave functions, you have a real and imaginary wave function that's talking about how bright a particular state is. And what you see, what happens with the mathematics of this, is you get a Gaussian, a normal distribution for the real part and the imaginary part. The brightness, the probability, is proportional to the radius squared, okay? And then it turns out that with a normal distribution here and here, you get an exponential distribution looking this way. So this is a computer-generated data for about 20 qubits, about 1 million states. This is the index K of all the 2 to the n states, and you see the probability bumps up and down here according to this. You see a lot of states at low probability and fewer states at high probability. And in fact, if you were to just sort this from low to high probability, you would get this curve. And if you tilt your head, you see that's an exponential probability called a Porter-Thomas distribution in quantum mechanics. Okay, so that's the speckle right here. What's interesting is if you have an error in your circuit, so you flipped a bit somewhere or you flipped a phase, you had an error, then what happens is you no longer get the speckle, but you get a distribution as if you had incoherent white light going through that, and that's a uniform distribution. Again, with one error, you lose your speckle, and it looks classical. I mean, that's what you would guess classically, that every probability is the same. Okay, so with that in mind, you can actually do some calculations on what you expect to see in it. Now, I want to back up. We've talked about this before, but quantum computers have errors. And a lot of times it's hard to remember that because the computers that we are using these days are so good, we don't expect them to have errors. And in fact, every once in a while, we have an error, say, in the operating system or somewhere, and we see the blue screen of death, and everything's horrible. But that happens very rarely. The problem is with the quantum computer, these errors are intrinsic. They're going to happen, and you have to reduce the errors as much as you can so that it's going to operate properly. And there's a whole thing that we have to do that. Now, what's nice is if you want to know what this cross entropy is, you just average the entropy due to the quantum and due to the classical, and P0 is the probability of no error. It's just basically the total number of errors. So it's not too hard to calculate. So for this experiment that we want to do, we're thinking about making about a 7 qubit in X and 7 qubit in Y, about 49 qubits. In order for the entanglement, for the logic to go across the whole array, we have to do about 7 layers deep. Okay, so that's about 350 total errors. And if you take the 0.5% error, which we know we can get, we've gotten that in a 9-qubit device, so we're pretty sure we can do that, the number of errors is about 2, 1 or 2, and either minus 1 or 2 is a big enough number that we think we can do that. So we may have to improve this a little bit, but basically we're saying that, you know, the experiments we've done in the past kind of indicate that you might be able to get this to work. So we've done some experiments. We're not quite there at a quantum supremacy experiment, but we did do this on a 9-qubit device to test the basic algorithm. Okay? And in this particular case, we did it a little bit differently, but for 5 qubits, what we did is we ran the experiment so that the final result would be with 2 excitations, 2 photons, distributed among the 5 qubits, in which case there's 10 possible states here. And what I plotted here is the probability to measure all of those 10 possible states for one particular instance, okay? One particular set of randomly chosen gates. We get some distribution, then we change the particular gates we choose, we get another distribution, and another distribution. Now, I just want to say, by looking at this distribution, where there's lots of small ones and a few big ones, you immediately see we're seeing a speckle pattern. It's not uniform all the same probability, what we would expect classically. Some are small and some are big, okay? And you can actually look at the statistics of this to measure that very carefully and show that it was going there. What's even more interesting, of course, is compare with what you expect, which is, in fact, the dots. So those are the probabilities that we calculated with the classical computer, knowing what all the gates are doing. And it's very nice. You see where the measured probabilities are low, the model predictions are low, and where it's high, it's high. And same thing for this instance, and this instance, and this instance. So we've been able to predict exactly what this speckle pattern should be, just by calibrating it and knowing how everything should work. So one can be a little bit more quantitative in that and talk about this cross entropy now normalized so that 0 would be a random guess and 1 would be a perfect prediction. And then we can also talk how many cycles deep we had to do it, from 1 to 10. And we see that the fidelity is pretty good. It's 95% here and going down to about 80% down here. As you have a longer and longer thing, there's a greater chance for there to be an error. So this going down linearly makes sense. And basically it says that you are looking at that very, very accurately. Okay, that's for 5 qubits. You can also do it from 3 all the way up to 9. As you have fewer qubits, there's less chance of error, fidelity's higher. More qubits, the fidelity is less. More or less scales as the number of qubits. And what's nice about this is you can get out a number of how well your circuit is doing. And in particular, it's about 0.3% error per gate and per qubit. And, that's kind of in the range we need to do something. Now, this is for 9 qubits. You see it's more or less proportional to the number of qubits. What would we see if we had 45 qubits, okay, which is at the limit of supremacy? So if you just take this and assume that it's going to continue scaling linearly, which may not happen, okay, you have to test that. But, okay, this is kind of going on here. You can say that. And it would be more or less this line right here. So given this is significantly less different than 0, this would say that the quantum supremacy experiment looks like it may be possible when we scale up to this thing with some kind of margin. Things can get a little bit worse and it still would work. So we're very excited about pushing forward. Of course, we have to do that. And I talked about how we're working on that. I do want to talk a few minutes, not just about trying to do something powerful, but also trying to do something more useful to simulate some physics that we might be interested in. So we took this device and we used the supremacy to calibrate it and check it really well. And then we ran an algorithm. And this is an interesting, simulation. This is an interesting simulation that maps to a 2-dimensional sheet of atoms, say a graphene sheet of carbon, that's put in a large magnetic field. And for a given magnetic field, we want to know what the energy eigenstates, the oscillation frequencies. And we're going to do that for 9 qubits, 9 lattice sites, because that's what we can simulate. So if you run the computer calculations for each magnetic field, you get a series of frequencies. You change the magnetic field, and you get these curves here. Note that this is a normalized magnetic field. This magnetic field for real materials would be about 10,000 Tesla. That's not something you can build in the lab, so it's kind of nice to be able to simulate that. And this kind of structure here is called the Hofstadter butterfly, which is very interesting because you see big changes in the energy which kind of form energy gaps, and you see a lot of structure in here, both fine and small scale, and you're basically looking at a fractal behavior of these energies. So let's just take this problem and run it on our quantum computer, okay, and see how well we do. And we map this Hamiltonian, this physics, onto our qubit, calibrate the qubit, and then just run it and see if we get the right answer, okay? And look, you know, there's all this structure in here, right? We really gonna be able to pick all that out? So at a given B field, we run that, get the energies, do the next B field, sweep out all this. And if we do that, there are the dots. And unfortunately, you can't see the theory anymore because it got erased by the projector. What you would see if you had the theory lines is that all of these dots are going through the theory lines. I mean, look at here, it's going up and down here, it's going up and down here. In fact, the difference between the experiment and the theory is given by the colors here, and you see most of the colors are black, which are a few megahertz, and green, 5 megahertz, and this is on a few hundred megahertz scale. So we're accurately predicting what's going on within a few percent, okay, running this complicated algorithm and sweeping over all these parameters here, and we're seeing all the details here very, very accurately. So this really shows that, you know, we can do quantum simulations, test quantum physics using this, and get enough numerical information to do something useful. So that's kind of nice. Of course, this is still a toy model. It's easy to calculate this with a classical computer. We have to combine that. We have to scale up and do that. But it's very, very hopeful we can do that. I'm basically run out of time, but I do want to mention one thing here about theory. We're really excited about the possibilities of using these quantum computers to solve real problems. And particularly interesting algorithm that other people and we are looking at, of course, is quantum chemistry, okay? And here's a table of kind of the process of what's been going on with the theory algorithms over time. In the 80s or so, Feynman, of course, came up with the idea of trying to solve quantum problems with a quantum computer. And that was very seminal and important, but it took something like 20 years for people to start getting a grip on the problem and figuring out how to do that. And at first, there were very general theorems that said it's not exponentially scaling, which is good, it's polynomial. And then over time, it became more and more clear what to do. And finally, in about 2013, you had a specific algorithm worked out so you could tell what the scaling would be. And in fact, at that time, the scaling was order n to the 11th, where n is kind of the size, more or less the number of orbital basic functions. And I'm sure everyone here knows, you're savvy about this. Not physicists don't necessarily know this, but order n to the 11 it's polynomial, but n to the 11 basically means it's not going to work, right? Okay, and you can see that number of basis functions. You produce something useful, it has to be between 50 and 100. And then the circuit depth scaling, which is this, more or less given here by our superconducting qubit numbers, and to the n to the 11 scaling means you'd have to run this for the age of the universe. Not going to work. Okay. But people kept working on it, and notably the Microsoft work. And down here it got to n to the 6 or so at least it was days or weeks or something like that. But in the recent few years, there's been continued progress coming down here. Now we think that if you choose everything right, you can have an n to the 2.7 or n to the, for an exact, or n to the 1 for an approximate. And this could be done maybe with physical qubits. This needs error-corrected, maybe 1 million total qubits, but it's in the right range. So if you look at n to the 2.67, n to the 1, you're looking at, let's say, sub-seconds if everything works out right. This is really exciting because it means that, yeah, okay, you may be able to do that. Still has to be researched, make sure this is going on okay and working properly, but it's really kind of exciting that this may be a real application. Note that a lot of this done was this Babish guy. Google hired him. We were taking notice of what's going on. So he's kind of working with us now to try to figure out how to build this thing. So maybe now possible. Okay. So I want to kind of conclude with just saying that we built these 9-qubit devices. They work really quite well, and we can run very complex devices and get it calibrated. We have a 22-qubit device in test. And okay, we still have to check everything, but it basically looks like the performance of this is going to hold. We'll have to see. And we're pretty excited that we're fixing problems and things are better. So we kind of think we can build a Supremacy device. And in fact, we're hoping to build something by the end of the year. And then also what we want to do is take that device and, like D-Wave and IBM, offer that to the outside scientific work through a quantum cloud offering so that everyone can do that. So I want to kind of summarize and end here with something that's a little bit my personal thought, and I think it's a little bit speculative, but it's kind of an interesting thought. And the idea here is that the software industry really expanded when students could get on classical computers in about the 70s or so and gain their 10,000 hours of experience writing code and knowing how to build things. And we're hoping with the opening up of the quantum computer to researchers via, these cloud kind of services, hopefully maybe some of you scientists in the field can start thinking about these problems, and we can increase the generation of ideas for the algorithms. And this is kind of the final idea I would like to leave you with, is if we can get this powerful quantum computer to work in the next 6 months or so with the Supremacy experiment, at that time, we are just one super clever idea away from doing something useful and then really changing our field. So, I invite everyone to help us go find that if it's out there. So thank you very much.
Okay, well, we're going to now have a question and answer session, for which I'm very glad to discover we have longer than I'd anticipated. We have until 4:30. We have an hour. So if I can invite all of the speakers to come up and take their seats, and the questions will be open to all of you who I hope have been saving up questions until now. I just wanted to kick off and to address a question to all of you. You don't all have to answer, but, and John, you've kind of started touching on this already. You've all been working in this area for long enough now that you will have a sense, I guess, of how things are headed. And I'm wondering whether you're thinking, great, it looks like we're all on course, this is going pretty much how I'd hoped it would, or are you thinking, my God, we're here now. We have prototype, admittedly, but we have working quantum computers. They're, in a cloud-based system. We're simulating beryllium dihydride. This is really taking off. Or are you thinking, okay, we have these toy devices. I don't know how the hell we're going to solve the huge problems that are looming in order to deliver on this promise. Where on that scale do you stand?
We're in a superposition of those two ideas.
Don't look at him. He'll collapse it.
Yeah, don't look too carefully.
Right. Well, I mean, I never promised the huge devices, so that's someone else's problem.
Right. But others have, yeah. And someone has got to deliver on that.
Yeah. Well, I mean, I'm pretty excited about where we are right now, because I think, for a while it was pretty much the academic research world and then D-Wave. you know, which is this one startup company that, you know, makes, you know, claims that, you know, sometimes I would have to respond to on my blog. But, you know, within the last few years, it's become much, much richer than that. There's, you know, these big efforts that we heard about at IBM, at Google, at Microsoft. There's, you know, this whole profusion of startup companies, and, you know, I'm optimistic that we'll be able to achieve this supremacy. By the way, John, when you said the end of the year, you don't mean the end of the calendar year, do you?
We hope to build a device by the end of this calendar year. Oh. And of course, testing it and getting it to work is really hard. But we're testing all of our stuff right now with 22 qubits, and we have to see how it goes. But
wow. All right. Well, you know, in any case, in the near future, you know, I think, you know, we will pass this milestone, and then after that, you know, we can start thinking about doing useful quantum chemistry simulations, physics simulations, you know, and then further out into the future, you can start thinking about the universal, programmable, fault-tolerant quantum computer. You know, and it's that third step that I don't know how long it's going to take, and I wouldn't want to, you know, have to wager my own money on it. But in the meantime, there's plenty of exciting things that are happening.
Okay. Do we have microphones, by the way, to a roving mic to address questions? Yes, thanks. There's a question at the front here, if we could bring a mic here. Sorry, just in the front row here. Sir Michael, in fact.
Well, let me first say I greatly enjoyed all the presentations. I learned a great deal. I have essentially one basic question. I live in Edinburgh, which has actually, you may not realize, we have a place which has 500 different computer scientists, and we're going to have another 100. And I also have next to my office a place doing physics at extreme conditions, where they study things at extremely high pressure and things like that. And I've learned from them that there are new things happening in the world of those conditions, not fully understood, but and they involve studying things made out of helium and related things. And I've got interested in the mathematics of those as well. And so it seemed to me that was the area where some radical new possibilities might emerge. Anybody had any comment on that? Do you know about the work that's done there? Well, I think it's been done all over the world, and billions of dollars being spent on it, some of it probably spent by you guys, or at least your bosses. And it is extremely interesting because it may open the door to really radically new approaches to all this computation.
So this is what they call hot dense matter, isn't it? They call this, it's often called hot dense matter, the sort of stuff that you find in the interior of stars and planets.
Done in diamond anvils,
yeah.
And extremely high pressure, and in an area where none of the basic physics is understood. And they do vast amounts of numerical simulation to get numbers, and millions of dollars are spent by all over the world. And as a mathematician, I don't feel that's the right way. There should be better ways. Understanding that the physics at extreme conditions is not covered by anything. Ordinary quantum theory sort of has not much help at all. And so people guess, and the guesses are really wild. And I think, well, I hope that the mathematicians can contribute to that by showing better ways, including topological methods, which help to produce stability in these systems. And if that's the case, we were able to do things a little bit more cheaply than they do now.
May I take that? So, I mean, in principle, of course, quantum computers are very good at that. So, quantum computers for simulating quantum systems can be used not merely for looking at chemical systems, but for things like, you know, matter in extreme conditions like quark gluon plasmas, or even if you have a model of what happens inside black holes, you can do that as well. But the ones, if you were looking at just these matter in extreme conditions, then I wonder, that's a good question about how many quantum bits you need actually to simulate something like that. I suspected. I'm sorry?
So if you're saying that you think that these phenomena would violate quantum mechanics, I mean, I think, I would just, comment that there's been a century of phenomena that people find in physics that they don't understand, and so far, in every case, they've been able to fit it into the framework of quantum mechanics. If ever we find a case where that doesn't happen, whether it's this hot, dense matter or something else, I think that will be a revolution in physics, and we'll look forward to that. Yeah.
At the moment, there's no good theory that enables people to get good answers in practical terms without a vast amount of experimental work, and that only gets you so far. There must be a better way of doing it.
Well, but having a quantum computer does give you a theory, in the sense that if you actually have a notion of what the Hamiltonian of these systems is, and then you can actually. Well, but that's going around in circles, or rather, going around in circles or in a spiral is actually how you make progress in physics, by a combination of modeling, experiment, modeling, experiment, modeling, experiment. So, I mean, it's not in order to understand what's going on in these systems, you have to have a model. It's actually as you said, it's very difficult to have models of this hot, dense matter. The ability to make new kinds of models, for example, with a small-scale quantum computer, would be a great thing to be able to compare with the actual experiments. So it would give us new ways of making advances in these systems. These complex, high-energy, high-density systems are indeed very difficult to understand. And one of the reasons they're difficult to understand is that they're systems where our ordinary, physicists only have a few mathematical techniques, which I think you're asking us to have more, like more topological techniques. Right, all distributions are Gaussian, and we only do things where we apply perturbation theory. And if we can't apply perturbation theory and it's not Gaussian, we model it that way anyway, and then get the wrong answer.
I mean, it makes me think another area where this might be relevant is in what people are calling quantum materials, where these are materials where quantum mechanical properties don't go away. You've got to deal with them. Things like topological insulators. And this area of condensed matter physics it's absolutely huge, and it needs to be modeled. And they are intrinsically quantum systems. And in fact, we've already sort of seen, glimpses of that with people modeling graphene, which is kind of the flagship quantum material. But there are a huge range of others. So presumably here too, this is an exploding field that quantum computing could have arrived just in time for, really.
Well, quantum computers are closed systems, so the idea of a temperature is not necessarily irrelevant. I mean, there is thermal noise in any real system, but in all these systems, when you apply a gate, you're driving it way out of equilibrium. So we don't have a language of statistical mechanics. We don't have a temperature, so.
Yeah, I think the part that I don't understand in your question is, well, I understand your question, but without knowing the models, is it that we have a way to model that, or are you trying to make the model? In the presence of temperature and pressure, maybe that's something outside of what Chris is saying in a small model that we need to put ideas in. You could imagine with quantum trying to engineer how it interacts with its environment, but that's all stuff that we are just don't really have a good answer. But I think you need to understand what the model is first.
There was a question in the middle. In fact, there are two now. If I can take the one on this side first. Yeah, just in the middle there, the chap with the raised arm. Yes, yeah.
Hello, thank you for a non-hyped version of quantum mechanics. There's a lot of hype around. So a double-barreled connected question. We looked at two hardware approaches to quantum today. Are there any reflections on other hardware approaches, namely doped semiconductors or the topological approach that Microsoft's pursuing? And is it true that the classical systems that will be needed to communicate with the quantum systems, they're agnostic about the hardware that produces the quantum computer, or do they influence each other?
Well, okay, so there are, I think it's, though it's, at the moment, I would say that the ion traps and superconducting systems are the ones that have really proved their worth and demonstrated this near-term scalability. It's certainly not too late to give up on other types of approaches. I mean, atoms doped in silicon is an old idea dating back to Bruce Kane, and the original proposal, which was followed very closely in Australia in particular, turned out to be very fragile. And if you moved one of the atoms over by one atomic unit in its silicon lattice, then you changed their couplings dramatically, and this turned out to be too fragile in order to make it work. There's a new proposal to make this more robust, but it's just a proposal. No experiments have been done. And topological systems also, it's a lovely idea, topological quantum computation, because topological quantum computation is intrinsically protected against errors. At the same time, it's hard to build these systems. I have this empirical, this is just an observation over the years. I mean, I've been working and building quantum computers with people since prior to Shor's algorithm in 1993, 1994. And one thing I noticed is that when people come up with a new model for quantum computation, that the promise of this model is inversely proportional to the number of experiments that have actually been done. So before you do an experiment, the promise is infinite. So a few years ago, speaking of topological insulators, Frank Wilczek came to me very excitedly, said, "Seth, if quantum computer is ever built, it will be built with a topological insulator." And because it hadn't yet been demonstrated experimentally, of course, it's like it has infinite promise at that point. And then when people get to the nitty-gritty of seeing what you actually have to do and deal with, actually building bits and coupling them together and getting the information out, you find that it's more difficult. But it's certainly too early to give up on these other proposals. But if you haven't yet built a quantum bit using a method, then you are 15 years or 20 years and $1 billion behind. So you're going to have to work to catch up.
I wanted to just add to something that you kind of were mentioning, scalability. But it's very important to look at the controllability and the error rates of so it's kind of two axes. It's quantity and quality. And I think in the superconducting qubits and the ion traps, we've been able to control the qubits really well and keep the control even as we start scaling it up. And, I think in the semiconductor qubits, for example, the single qubit gates are pretty good, but when you have two qubits, not so good. And that's because there's some charge noise around there that's moving these around and causing it to not work so well. And that's something they really have to work on trying to solve, I imagine, among other things. So it's, if they can solve it, they have a great system. But you have to solve those kind of problems to get the technology to work.
I mean, you also could have mentioned photonic quantum computing, quantum dots, right? Several other things. I don't know. I feel lucky that as a complexity theorist, I don't have to bet on any of these, but can just talk to my friends who do each approach and hope that at least one of them succeeds.
But there was also the part of the question about whether what you surround the quantum computer with and the classical parts of it, how dependent are they on the hardware that is the qubits themselves?
There are similarities. Some things are different. Ions are using lasers. We're using microwave. The dots are in the microwave regime. It really depends how much energy it requires to excite a qubit, how much energy is coming out. And then there are similarities. If you got to go up to optical, it's a different.
If I could take the question, the gentleman in the striped shirt first of all, and then there's one over here. Thank you.
Thank you. Could you comment on the idea that quantum computation figures in the fundamentals of physics itself, and how research into quantum computation might illuminate fundamental physics.
We're looking at you. This is a really interesting question, and recently there's been a lot of interest in so string theorists who for a long time have claimed that they have the theory of everything. Again, it's one, if you can't calculate or predict anything, it's easier to say you have a theory of everything than if you actually do predict things. Have become very interested in connections between quantum coding theory and quantum gravity in the form of the ADS-CFT correspondence. But you know, this relationship goes back much further. If you look at, I was a graduate student in Cambridge University in the early 1980s. I took Stephen Hawking's seminar on quantum gravity, and many of the ideas about entanglement came out of the community of doing quantum field theory on curved spacetime, because you know, Hawking radiation, which says Hawking's famous result is to show that black holes are not black, but they actually radiate radiation with a particular temperature. And what's going on is that you actually have a pure state of the system that's not actually a thermal state, but it's in the state of the vacuum is entangled inside and outside this black hole. And so you have a beautiful entangled state. And only more recently did people in quantum information start looking at that. It's the thing about quantum information theory, it's a universal language for finite dimensional quantum mechanics, right? So that's, I think, one of the most wonderful aspects of this field is that this really became clear over the last few decades. And as a result, you can apply quantum information theory to all kinds of different fields. A few years ago, Physics Today had a centerfold, not for, I believe that there's a centerfold, a website called Stud Muffins of Physics, but this was not that. It showed all the subdisciplines of physics, and they looked at the overlaps between them, a number of mutual citations. And quantum information sat exactly in the middle of this because it was citing and being cited by all these other disciplines in physics, including things like quantum gravity. Nonetheless, we're still, you know, we're very far away from having a theory of quantum gravity, but it's clear that there are lots of overlaps, and at least we can hope that we might have a fundamental theory of what's going on based on quantum information.
I wanted to mention something interesting. I started doing this way back in graduate school because I was very interested in understanding how quantum mechanics work and testing it and the like. And what's kind of amazing is after you do these qubit experiments a while, the results of the experiments are no longer strange. It's just what nature does. And it's like, you know, you understand F equal ma by using objects and doing experiments when you were a kid on how things work. After you use a quantum computer for a while, the quantum mechanics becomes just something that nature does, and you kind of understand that in a way that you do classically. So I'm going to say that I think in the future, especially when quantum computers are really available, where they're beginning to, then maybe this is the right way to teach quantum mechanics to students and give them the intuition. And then the hydrogen atom and all these other physical things will be this kind of special case that's really kind of complicated or weird, but people are going to get an insight of how nature works from quantum information. And I think that's going to help physics.
So I would take out the maybe from what you said. I mean, I guess, you know, I'm in, you know, in a younger generation, right? But like, I came at a time where like this was just clearly, obviously, the best language to talk about quantum mechanics itself. You know, I like to joke that quantum mechanics is like, turns out to be really surprisingly simple once you take the physics out of it, right? but then, you know, once you have this language, you know, it's no surprise that you can then take it and apply it back to all sorts of issues within physics. You know, and as Seth was saying, within the last 5 years, there has been this remarkable connection made to issues in quantum gravity. The leader of that has sort of been Lenny Susskind at Stanford, and a bunch of others have been working on this. And, you know, there's a few reasons for it. When you study the black hole information problem, you know, and you start worrying about things like this firewall paradox that was discovered in 2012, right? You find, you know, actually, in some sense, some of the main issues here are literally issues of complexity theory, right? They're issues of, you know, you could, in principle, apply some unitary transformation to the Hawking radiation that's come out of a sufficiently old black hole, such that, you know, if you do it, you get the prediction that you would just completely destroy space-time, like at the event horizon of the black hole. Okay, but then you can think about it more and say, you know, that computation seems to require exponential time to perform, even for a quantum computer. Okay, so a black hole, you know, the mass of our sun would evaporate after a mere 10 to the 67 years or so. Okay, but to do the kind of computation that, you know, is involved in this firewall paradox that would sort of threaten space-time, that seems to require it's more like 2 to the 10 to the 67 years. Okay, so, you know, maybe, you know, the black hole would have long ago evaporated before you'd even made a dent in it, right? So, you know, so you see like computational difficulty sort of protecting geometry in some sense. You know, other connections come from ADS-CFT, where you can look at some very natural geometric quantity in the bulk of a space-time, like the volume of a wormhole, you know, between two regions, which is just expanding according to, you know, general relativity. And then you can look at the dual of that, you know, in this, like the holographic dual on the boundary of ADS space. And what you find is the dual to that is just a quantum state that continues to get more and more and more complicated. You know, so then you have to say, you know, the only thing we can think of which is dual to this geometric quantity in the bulk is some sort of measure of complexity, which, you know, Susskind has advocated using literally the circuit complexity of the state, meaning the minimum number of quantum gates that would be needed to generate this state. And there's some evidence that, you know, I don't know if it's causal, but there is at least a very strong correlation between the two things. So I don't know where any of this is leading, but I do think it is, you know, it's certainly been striking to me how the concepts of quantum information have suddenly, you know, shown up, you know, in fundamental physics to the point where the string theorists are now at our door, you know, to ask us questions, you know, and it's been interesting enough that I've sort of felt no choice but to get someone involved in it, at least as a computer science consultant.
Scott, you mentioned Len Susskind. It's very striking to me how he's brought out this fantastic book, Quantum Mechanics, the Theoretical Minimum. And so it's basically sort of saying this is the minimum you need to understand quantum mechanics. And he starts talking about the quantum mechanics in just the language that we've heard today, about manipulation of qubits. Right at the end, you get to quantization of the hydrogen atom. And that's, you know, it's a real inversion, I suppose, of how it's traditionally been taught. And I find that a very striking reflection of how things are going.
That's a beautiful book. You know, by the way, Feynman more or less does it that way in the Feynman lectures,
right,
even.
Yeah, it's you know, people teaching physics teach physics. I learned physics the same way that people, you know, learn physics now, and it's also the same way that people learned physics in the 1930s. There are 5 papers that Schrödinger wrote in 1925 to 1926, starting with, you know, Schrödinger equation, particle in a box, harmonic oscillator, leading up to the hydrogen atom. And that's the way almost everybody learns physics. And that's a much harder way to learn about quantum mechanics than it is just to look at quantum bits. In my introductory course in quantum computation at MIT, about a third of the students in the course are mathematicians who have never taken quantum mechanics. So we have to have 2 weeks at the beginning of the course to teach them the quantum mechanics of two-level system, and then that's it. Then they're fine. They're good to go. It really, once you phrase it in terms of, well, I mean, it's like, I have several books on my bookshelf that are the mathematics of Hilbert space, and they're these thick books like this. But if you were looking at the mathematics of finite dimensional Hilbert spaces, it would be one page like that. So it's much, much more simple than it is to do it in the traditional way, and much more accessible.
Right. Questions? Yes, there's one here. We've got a microphone.
Okay, so first of all, thank you very much for all the talks. They're very instructive, even for non-specialists as myself. But one point that was a little bit confusing for me is that, like, it seems that it's very hard to control even like 22 qubits, 6 qubits, but on the other hand, we're thinking about like going to the big data world that needs, I don't know how many. So I'd like you to comment on the perspective of scaling this up to the big data world. And on that matter, this is more of a curiosity. So how do you really like store, copy, and query data quantumly, or how can you build an interface between the massive classic data that we have and that enables all these interesting applications that we are seeing in the late years and the recent years? How do we make them an interface between this classic data and quantum data, in a sense?
You don't copy quantum data, by the way, but the other things you can do.
That's right.
Yeah.
That's right. The no cloning theorem prevents you from copying quantum data. Yeah, that's a very good question, and I would say there are designs for devices that will take large amounts of classical data and turn them into a quantum state. That's to take n bits of classical data and to map it onto a quantum state that has log n quantum bits. Once you've mapped it onto a quantum state that has log n quantum bits, and there's all kinds of things that you can do with it, as I suggested in my talk. But I think it's an open question whether one can do this in a practical, technologically feasible fashion. It's probably easier than, I mean, as I mentioned, you can create a quantum state that encapsulates a large amount of data, but getting it into the form where you can pop it into your quantum computer is another question. So, I mean, we have patents and we have proof of principle demonstrations, but I wouldn't say that these are things that we believe can be scaled up right now.
I wonder if I can put that question a slightly different way to you guys. How many qubits do we need? It sounded like if we have 300, we model the universe. So
there's already 2,000 qubits out there in a commercial device. The problem is, how good of a qubit do you have? So it's a two-dimensional horse race. It's not just the number of qubits, but how good they are, and I think how they're connected is another. There are more things than that even. But just if you can people can talk about those two axes, I think that would be useful.
Yeah.
And you have to do both, and doing both at the same time is really hard.
Yeah. So I agree, it's hard. This is what we're pushing, but since I started in this field, we were doing 1 and 2 qubit experiments. It was more focusing on isolation. We've seen in the last few years really starting to, I won't say it's just tiling up, but you see that everything you learned from before, you can just take it and use it, and things are getting bigger at a much faster rate. So this is what gives me optimism about bringing this up. The 16 qubit that we put online is no worse than the 5. So we still need to improve the fundamentals, but it's all about just doing multi-qubit gates in multi-qubit architectures and really controlling the error rate and bringing the error rate down.
I might add that what I lose sleep over, I suppose, is if we have 400 qubits, is it useful? and this is not a scientific statement, but I do believe if we ever get to 1 million qubits, we actually have to find a useful application for 500. Because if there's no useful application for 500, nobody's going to pay for it. This is not a scientific statement. If we can get to 1 million qubits and science will not halt us, that doesn't mean we'll get there.
Yeah. Yeah, I mean, certainly, applications to doing things like simulating solid-state systems and many-body localization and other things that people are interested in, or in like behavior of matter in extreme conditions, 500 qubits will go a long way towards looking at that. But I'm not sure that there's a big market out there I mean, I myself have a few euros in my pocket. I'd love to have such a device to do it, but I couldn't pay you to build it.
Other questions? Oh, thank you. Yes.
Can you say something about what the timeline will be for breaking cryptographic systems using quantum computers?
I think, we wrote a paper on the surface code error correction, and in the appendix, we have a rough estimate. And for superconducting qubits, which are quite fast, it's 100 to 300 million qubits. For slower, if it's 100 times slower qubit, it's 100 times more qubits. So let's say billions of qubits. And what are we now at? 10? 20? But I would say that the people who worry about, the internet getting broken by a quantum computer are rightfully looking at the problem, and they're trying to develop quantum resistance codes so that this will not be a problem when eventually we might be able to do that. So I think we have time to solve the problem, but we have to start working on it now. But when I grew up, my dad bought a 5-transistor radio, and that was really amazing and whatever. And now, in my pocket here, what is it? This is almost a trillion transistors, for very little. So, these numbers, maybe we can figure out how to do it. It's going to take some time, just like it did for regular computers.
I mean, I think of threatening public key cryptography as sort of one of the last things to happen in the development of quantum computing, right? I mean, it's, at the point that you're doing that, you basically probably have a full fault-tolerant universal quantum computer that can implement, whatever algorithm you want. So I think, quantum simulation and even some of the machine learning and optimization, tasks potentially are things to look for before that. But the other point that people make about this is that if you have secrets that need to be protected for 30 years, then maybe this is something that you're worried about already. I don't know. If I don't really have secrets. I just put everything out there on my blog. But if I did have secrets, I'd probably worry about people stealing them in much easier ways than by building a quantum computer.
Yeah, I think it's important that people realize there's a difference between a fault-tolerant quantum computer and what we're doing now. Even understanding exactly what error-correcting code we will do, they're just good guesses. As we get these systems bigger, we'll look at different types of codes. That number could change quite a lot. It depends on exactly what we're trying to do. So at the moment, the focus is more on, as Scott said, sampling type algorithms, optimization algorithms. These are not ones that use the primitives that are used in Shor's algorithm.
I would say that the best guess of when we would have a full-blown, fault-tolerant quantum computing that would break RSA is somewhere between 25 years and never. I mean, it's possible that it might not be possible to do. I think that each stage along the way, they may be difficult. Luckily, I mean, it looks like it's possible. It looks like the problems are technological in nature. But they are daunting. I mean, as you say in your paper, it's like a daunting technological problem.
I would say that, I've been on some committees, and people who are in the banking industry and they worry about, the destruction of the economy from breaking RSA, they want to have this kind of fixed in a 10-year time frame.
Yeah.
Because, I agree it's going to take longer than 10 years, but they kind of want it, and that gives you some time to solve the problem properly.
I do think this will eventually happen if civilization lasts long enough. Whether it will or not being my main uncertainty.
Depending what you mean by civilization.
Right.
I wanted to ask you all something to pick up on. I was very struck, John, that you said, you echoed just what I'd heard yesterday at IBM about the fact that Google and IBM are putting the stuff out there, putting it out there, you know, in a cloud-based system for people to use, because companies need the ecosystem to evolve so that the companies can do something with quantum computing. And in particular, you need a young audience to be familiar with how to use this stuff in order for it to succeed.
I would say, I think we've touched on this already, that we have to develop the medium scale algorithms. And we think that I'm sure IBM thinks this too, to putting out a machine and having people play with it will help people think about it and get young people interested in doing this, and someone may come up with that great algorithm, because it's clearly a lot easier to play with it and start understanding it when you have a machine to work with. Mm-hmm. And that's kind of what our hope and strategy is, and trying to develop that and understand what's possible from it.
And it seems that that's something that's only been learned by the big computer companies that exist already from experience. No one thought that way in the 1950s, when IBM and the like were starting up. It's that realization that you can't do it alone. I mean, I'm just wondering if there are other lessons that have been learned from the classical computer industry that need to be extended.
I can speak from our perspective. So we put it out there. We did it in 2016. And there are numbers of reasons. Like, there are many theorists that want to come up with ways of coming up with verification techniques. Give them away. They can verify it. People want to learn. People want to see it. And this is why we're also going down the path of releasing some open source tools that you can control it. Is the faster we get it into the people that want to use it, start using it, they can explore what they want to do with it. We can learn from that. We can learn about the device itself. And one of the other reasons we did it is it's much easier to have an idea in an experiment, go to your colleagues and say, all right, we're going to do this. You cal it up, you run it. We wanted to answer the question, can we make something automated that it will bring itself up, stay reliable, stay online, and be able to be, like, we can still do better in the lab. We can tweak it a little bit better. And the fact that we've kept it up for over a year now says that these are very, very reliable devices. And this is a lot of learning that we needed to make as well. And it's all automated.
Yeah, and I would say D-Wave has done the same thing, and they've done it at user sites, and they've done it with their own cloud. It's a different machine, but there are a lot of tricky things about how that works. So this is all very good, that you're able to build real engineered systems and getting the whole system work well.
Yes. Another question in front of you.
There's someone in the back.
And there's someone, there's someone right at the back as well. Okay. So we'll take this question here first. Okay, yeah, I've got you.
It's really the last question for me. We've heard quite a lot earlier on this HLF about neuroscience. Now, undoubtedly, the big question for the 21st century is neuroscience. And there's some sorts of analogy between quantum computing and neuroscience. Both agree that they're enormous problems. We know it's the beginning in each case. Some people make more than analogies. Do you have any comments about the relationship between, or lack of relationship, between computer science and neuroscience, and which will solve the problem first?
I mean, there's been lots of speculation about maybe the brain is a quantum computer. I think right now, there are several difficulties with that proposal, right? One of them is just that, it seems hard for coherence to survive for, more than, for any neurologically relevant time scale in the sort of hot, wet environment of the brain. A second problem, is that the types of things that a quantum computer is good for, like factoring numbers, simulating quantum mechanics, just don't seem like a good fit for what would have been useful for us in the ancestral environment, right?
I was not suggesting that.
Yeah, okay.
think of it the other way around.
Yeah.
Neuroscience helping computing.
Well, I think to some extent it has through, the development of deep learning and, machine learning techniques have been indirectly inspired a huge amount by neuroscience. And of course now there's, a whole field within the last decade of quantum machine learning, which you heard about in Seth's talk, right? Of course, if the brain is not a quantum computer, then in some sense what you're doing in quantum machine learning would be not how the brain does it, but, a different way of doing it that also has advantages. I think, there's lots of room for analogies, but, I see papers, I have to tell you, I see papers on the archive like every month or so that say things like, oh, well, we're going to apply quantum mechanics to cognition. We're going to say, well, like when you were vacillating over making one decision or making another one. That's like quantum superposition. And it goes on and on about this. And I keep thinking, why not just say that you're vacillating? Why bring quantum mechanics into it? Yeah. I think for an analogy to be useful, you have to be able to actually import, non-trivial concepts from the one place to the other. And, so we have a high standard for that because in math and physics and computer science, we know so many examples where analogies really are useful and where concepts really do get imported in a powerful way. And I think between quantum mechanics and neuroscience, I feel like I'm still waiting for that. Yeah.
There was a question right at towards the back there. Yes, thanks. You've got your hand up. If you could keep your hand up, we'll get the mic to you.
Way in the back.
Just on this side. There we go. Thank you. This probably will have to be the last question as well.
Hi. So in one of the slides, I actually saw that you compared the first computer, which was a room filled, to similar to how quantum computers are right now. I know it's really early stage, but if you look at the early computers to computers that we have in our pocket, they're about 10,000 to 1,000,000 times faster, cheaper, smaller. Can you make a comment on how you see quantum computers which require near zero temperatures to work, to how can we put a timeline or some thoughts on how soon we can have a quantum computer as a PC even, or maybe a smartphone?
Why do you want it as a smartphone? We have, the whole point of a smartphone is it's connected to the internet. So why not just, if you ever need to simulate a giant molecule or factor a huge number, why not just upload it to a quantum computer that's in the cloud? By the way, apparently Ken Olsen said, there's no reason for anyone to have a computer in his home in the 70s, and everyone ridicules that as one of the wrongest technological predictions of all time. I think he was just too far ahead of his time. Eventually, yes, you put the computing in the cloud and just tap into it.
But actually, just going back to what you said, it's infeasible for us to say that that's not going to be useful like 25, 50 years from now. Nobody knows what kind of applications we are looking at that point.
Actually, this does bring up both what you're asking and Scott's comment brings up something which is we haven't talked about at all, which is a lot of the applications of quantum information are not just to computation, but to communications and to precision measurement and sensing. So I actually think that if you combine, once you combine, and there are many advantages to doing communications in a quantum mechanical fashion if you can do it, which isn't easy. But then John Wei Pan just recently did an experiment where they distributed entanglement from a satellite over a distance of many hundreds of kilometers. So it's something that's going to be happening. And then sensing and the limits to measurement are all given by quantum mechanics, and to attain those limits you actually need to make things and put things in entangled states and squeeze states. That's the next step for LIGO, the gravitational interferometer, is to inject squeezed light in it in order to attain its true capability. So I can actually imagine that if you're using a smartphone, by the way, I think that smartphone, there's a danger, the reason smartphones are a danger because the total intelligence between you and your smartphone is a constant. So as the phones get smarter and smarter, then it sucks intelligence out of you and you become stupider and stupider. So you have to be very careful. Just
I've been losing intelligence independent of my phone.
Yeah, I know. So that's even a bigger problem. But for instance, if you had quantum sensors, quantum random number generators in your smartphone, and it could be hooked up via some quantum communication, then I think that there would be a very good reason to have that. I don't know what it would be.
Well, I don't know about you. I've been wanting to see a panel like this and a session like this for a long time. So could you join with me to thank all of our speakers very much for what they've given today?